So then let's start with the first speaker of this morning. It's a great pleasure to introduce Silvia Villa who is an associate professor in mathematics in Genova and also a principal investigator at Malga, which is kind of machine learning at Genova. So the stage is yours, Silvia.
Thank you, Matthias. So thank you very much for the invitation. It is really a pleasure to participate to this workshop. As we were saying before, it's a pity that I was not able to come, but I hope it will be possible next time, maybe. And so also I hope the talk will be fine, even if we are a bit, so there are many online talks these days. Okay, so the paper I'm going to, the work I'm going to present is about iterative regularization. And in particular, the topic I'm going to speak about today has been largely Maturan Massias. So the problem we very often want to solve in inverse problems and machine learning is a problem having this form. So in the minimization of a function R of x onto a set of linear constraints ax equal b. So I assume this. So this will be the main problem of interest in this talk. The linear constraint is in an infinite dimension between infinite dimensional spaces, so we don't need to be finite dimensional, and is though linear. And R instead is a regularization function. From now on, I will always assume that belongs to the range of A, so that the constraint set is non-empty. And I will relax this assumption towards the end of the talk, but at the moment, just to simplify, also to simplify the presentation, I will stick to this case. So even if this is in a sense a theoretical point of view, let's say a bit abstract point of view, as you know, this kind of setting is suitable to deal with the solution both of inverse problems and learning problems, as I was saying before. And classically, very often, the regularization function has been chosen to be strongly convex. This is why this is due to the fact that the setting we are interested in is the one ax equal b as more than one solution system, and so the regularization function helps to choose one. R is the regularization function, and convexity enables us to do that. I will call this unique regularized solution X dagger. However, the role of the regularization function is not only to select a certain suitable solution, but so it is to select a suitable solution, but also to impose and in the applications, I mean, last 20 years, the regularization function is of regularization functions of interest are very often not convex, but only convex. So some examples I think all of us are L1 norm, nuclear norm, effects isometrics. Let's say that the regularization is less clear in the sense that we are not going to select just one solution. We will be happy with every solution minimizing the regularization function. We can observe, since we can observe that the regularization function is not strongly convex, but is only convex, and also this is just a technical difficulty, but not relevant for the I was doing is very often non-smooth. So I talked until now of applications to the inverse problem setting, but very often that we have to solve when we solve an inverse problem is not the one that I described, in the sense that in real applications, we don't have access to the B, so we don't really want to solve this problem, but we really would like to solve this problem, but having access only to a B delta, which is a noisy version of B. So in this talk, I'm going to assume to characterize this noise in this form. So assuming that the norm of B minus B delta is less or equal than delta. So in a sense, I'm dealing with the worst case scenario. Okay. And so the main an inverse problem is to recover a solution of this problem here, which is the idea because starting from B delta, in a sense, we want to, B delta can be interpreted as a perturbation of B, and we want, starting from B delta, to recover in a stable manner a solution of the ideal problem highlighted above. And there is a very classical way to do that. Maybe it is not the only one now, but for sure it's the most classical one. And it is the explicit regularization framework, the one that we all call Tikhonov regularization one. So that is that when I pass from B to B delta, I need to relax the equality constraints, since I don't want anymore AX to be equal to B delta. And this is usually done by introducing a data fit term that here is called D. And so relaxing this, and the role of the regularization is to, again, favor solutions making small dr, and is imposed by adding the regularization term, which is suitably weighted by this regularization parameter. So for, let's say, the regularization theories approach is, from the theoretical point of view, very well understood. So in the strongly complex case, this regularized problem has a unique solution. They call X delta lambda. There's some technical assumptions, technical condition here. And under this assumption, so if I call X lambda the solution of the regularized problem, delta lambda and X dagger here be bounded which is there is a bit of delay, at least for me, between the video and the yeah. So this is the thing that you can see here.
Silvia, can you hear me okay?
The quantity that depends on delta.
Maybe use
Sorry?
the direct chapter. And just like get her to disable her video.
Exactly.
Just
So
audio. So
yeah. So Silvia, could you like disable your video? We've got a quite poor audio connection.
Okay. So I close my video.
That would be great. Yeah.
Okay. Okay. Sorry.
Thank you so much, Silvia.
Okay. I'm sorry. I'm at the university. I was hoping for a good connection, but maybe it was better from home. Okay. So as you can see here, we have let's say concurrent terms, in the sense that there should be a trade-off between lambda to minimize delta over square root of lambda plus square root of lambda, and let's say the choice given noise level delta is given by lambda of the order of delta. And so for this specific choice of the regularization parameter, we can prove that the upper bound. So for the square norm, if R is the square norm, this is a very old result. For more general regularizers, this is a more recent result, is due in particular dealing also with general data fits. So this can say that let's say the theory is over, as we saw in this workshop. The choice of the regularization parameter is the for the solution of inverse problems, and there is still a lot of activity on methods, even very new methods, to tune the parameter. And but very often these methods are computationally demanding. As an example, this is maybe the most classic one. We want to set a parameter in practice. What we have to do is to, first of all, choose a regularization, let's say a suitable interval for the regularization parameter. And this is usually done by, I don't know, experience, okay? And then once that we choose the interval where the regularization parameter lives in, we have to discretize it. And for each lambda that we choose in this grid, we need to solve the regularized problem and then to choose the best lambda according to some validation criteria. Here there is maybe just a picture trying to visualize this. So we have the ideal solution here, okay? And this is the regularization path. So this would be the set of solutions of the regularized problem having access to the true B, but we don't have access to this path. We just can compute the red one, points on the red ones. And then on the red path, we want to select the point which is the closest to this blue line. We will do it with a suitable validation criteria. So as I said, the computations, this is really the key point. Once we have an efficient algorithm to solve the variational problem, and then we have to deal with that, with the fact that we don't need to solve just one variational problem, but we need to solve a family of variational problems. A quite old idea, which tries to answer to this demand for more efficiency, let's say a better efficiency from the computational point of view, is the iterative regularization approach, which is definitely a classic inverse interest in, for instance, the context of deep learning, the name of implicit regularization. So I'm going to introduce a bit this iterative implicit regularization approach and then to clarify what are our contributions. So in order, there are several ways to introduce iterative regularization. I want to use an optimization point of view, since it will be the one that we will exploit in order to results. So the point, the regular paradigm be expressed in this form. Again, we want to solve our ideal problem, the true B. So given the structure of this problem, for instance, R of x is a convex function, non smooth, Ax equal B is a linear constraint, we can select a suitable to solve this problem. And then we can call the so this is an auxiliary sequence, will never be computed because in practice we will never have access to it. Then after this we can do the same, so consider the same algorithm for the problem where we replace B with B delta. The structure, from the optimization point of view, the structure of problems is so we should expect there should be no difference in the behavior of the algorithm between the two cases. I call this iterates xk delta. And then a very naive idea, but that can be exploited, for instance, in the strongly convex case, is that iterations from the ideal solution using a triangular inequality. And then here I have two terms, this one, and they have a very clear interpretation in the sense that this second one is just a term related to the convergence of the algorithm xk to the solution x target. So to related to the good optimization properties of my method. And instead, the first term is a stability term, takes into account how much the two trajectories generated by the algorithm diverge, given that we are doing a non-zero error at each iteration, since we are using B delta instead of the true B. And in the convex setting I'm going to discuss later, maybe using this norm is not the best idea in the strong criterion, but the idea, let's say the underlying idea of iterative regularization, even in more general convex setting. Okay, so I'd like to, before starting, briefly discuss what are the previous results, because nowadays there is already a rich body of literature dealing with this kind of setting. And I was saying for the square norm, the approach is definitely classical. And so R of x equal to square norm, and then the iterative regularization, the most famous iterative regularization approach is the Landweber method. And this method has been extended in particular also to deal with nonlinear inverse problems and to the learning context in a series of papers. To pass from there are already some difficulties in passing, technical at least, in passing from the square norm to a general. First, choose a suitable algorithm, and very often the suitable algorithm, or in the known context of imaging, especially in a series of papers by Osher and Burger, Benning, the names that I remember, but there are many others. Iteration. And then there are also other possibilities. Later, in particular, known as Bregman iteration, and you can have also accelerated algorithms on the dual problem. And the results slightly differ one from the other, but I think this point is not relevant to discuss them. And then all of this that I discussed until now, if you want, works well with the least squares data fit. Instead, if we all know that the data fit is not just to enforce that AX is equal to B, let's say, in a sense that data fit impact that we are going to build. This gives considerably applications depending on the noise that is considered. So a diagonal data fit can be used. So what happens? So all of this works for strong functions, as I was saying. What happens in the convex case? So the results here are less, and in particular, looking around, it seems that the only general approach that can be used to build convex regularizers are the Bregman iterations or an ADMM algorithm. So this, and the point is that Bregman algorithm requires each step to solve a let's say a regularized problem. At least the form is that of a regularized. So it requires the solution of a non-trivial optimization problem. So basically, at the end, the algorithm would be done by two nested procedures. So from the practical point of view, this is for sure a limitation, a computational limitation. So after that, indeed, it has been, this approach has been generalized to the Bregmanized operator splitting, where this problem has been solved. And this Bregmanized operator splitting has used as a regularization procedure, even if we didn't find any critical analysis of its stability properties. So these are the starting points. What are our contributions? So we tried to devise an iterative regularization procedure, so for the convex R, and we using again an algorithm which is belongs to this family of first order methods, but is slightly from the previous one. Then I will present a special case, the case of L1 norm, where our general convergence and stability results can be analyzed, and I will show how to deal with the unfeasible case. So the case where AX equal B does not have a solution. And this is indeed a new direction, in the sense that has not been treated in other papers for iterative regularization approaches, except for the original Landweber one. So the idea is this one. We just because we can do it, and we have at disposal a very powerful. Non ci sono contenuti in riproduzione. Very powerful optimization methods. We take the regularization function as f plus g. Where f is a smooth path and g instead is a no smooth one. And the original problem can be written in the convex optimization language as the sum of the regularization plus the indicator function of just the function b, sorry, there will be, can you, right, sorry. And so this is the situation. So the function that we want to minimize is this one. So iota b is just the indicator function of the function of the point b, is plus infinity if ax is different from b, otherwise is 0. And so related to this, very often to study the minimization of these kind of problems, the solution of these kind of problems, the Lagrange function is very useful. And so I introduced it here. You see here y is the Lagrange multiplier. And the main assumption that we make is that there exists a saddle point of the Lagrangian. This is slightly more than assuming the existence of the solution for the problem P, since it involves also the dual variables, and is equivalent to this kind of first order solution. As you can see, this resembles the condition that the technical condition that was needed in order to prove regularization properties in the Tikhonov framework. So assuming that a saddle point of the Lagrangian exists, imply in particular that a solution of the problem P exists. So a very natural algorithm in order to split all the contributions of the involved functions is the Conda-Vu algorithm, developed independently by Laurent Condat and Bang Kong-Vu, where you can see this is I think it's a primal-dual method, so updating updating both the primal and the dual variable y, and it involves only first order information. So we have here the gradient of f, which is smooth, the props of g, and then we have instead this dual step that is related to the props of the dual of the indicator function. And it is well known that this algorithm converges, so iterates generated by this algorithm converge in a Weeks in the infinite dimensional set into a primal dual solution, so to a saddle point of the Lagrange, if the step sizes are suitably set. So we slightly generalize this analysis by allowing a preconditioning. So instead of considering just a step tau and two steps tau and sigma, we allow matrices T and sigma, positive definite. In the easiest case we have seen in the applications, it is useful to have a diagonal matrix since it allows to take different step sizes in different directions. And then we also allow inexact computation of the prox operator. So this prox here of G. Even if I have to say that the primal-dual framework gives very often the possibility of duplicating a variable, for instance, even in the case of total variation, to avoid inexact computations of the prox. But in case one does not want to the variables, because maybe they are already too many, can compute the prox inexactly. And inexactly in a strong sense, especially in the case of the stability results. So the weak convergence holds under these additional modifications. And then in our analysis, we want to study the stability of the algorithm where we replace the exact datum B by this noisy datum B delta. So our proof is based on the idea that this V delta is just another source of errors, like as the inexact prox, I don't know. So how to measure distance from optimality? As I said at the beginning, the norm is not a good idea since we are dealing with a problem which is only convex, and so only in special cases we can expect strong convergence of the iterates. So a classical way to measure distance from optimality is, for instance, to consider the Lagrangian gap, let's call it. So the difference between L of x y star minus L x star y. So for this special problem, where we have a minimization of a function over linear constraints, the Lagrangian gap coincides with the Bregman distance of the regularizer. And so this is the classical quantity that has been studied in order to get iterative regularization results. However, just sticking to the Bregman distance or the Lagrangian gap is not very satisfactory in many applications. Indeed, for instance, here we have a very simple example for L1 regularization. As you can see at a certain point here, after iteration 2000, the Bregman distance is between xk and x star is in practice 0, but as you can see above, okay, the norm is big, still xk minus x star, but maybe this is too much. We cannot expect that this goes to 0, even if we will see that is not true. It must go to 0 in the L1 case. And the other point is that this, again, also this inequality constraint is remains very big. So the idea is that, our idea is that the Bregman distance is not enough, for instance, for L1, but we would like to have something more stringent to assess convergence of the sequence xk, or at least to control the stability. And the optimality condition that gives us the idea on what to consider is this one. So it's very easy to prove that if we have a saddle point, okay, and another point x, y here, then if the Lagrangian gap corresponding to xy is 0, so this one is the quantity that is usually considered, plus this linear, the linear constraint is verified, then also the point, the couple, the pair xy star is a primal-dual solution. So in particular, X is a solution of the primal problem, because at the end we are interested in the solution of the primal problem. So a natural, two natural quantities that have to be taken into account to assess stability and convergence are the Lagrangian gap, but also the feasibility. So in our stability estimate, we indeed bound these two quantities, and we can prove that given the Kondavu algorithm, indeed, to be more precise, we need to average the iterates applied to the noisy datum. Then we can prove that the Lagrangian gap is upper bounded by this quantity, and the same for this feasibility gap. Note that here we have the 2B. So as you can see, as I was saying at the beginning, these kind of upper bounds are given by the sum of two terms. One which is due to optimization, so C1 over K can be thought to as an optimization problem, as an optimization error. It goes to 0 when k goes to plus infinity, plus a stability estimate, which is given here by delta plus delta square k. So as you can see, this quantity explodes for k going to plus infinity. Maybe I didn't stress this, but we do not assume that the noisy problem has a solution. We don't need to assume it. And the same kind of upper bound is true for the feasibility. And so starting from these two inequalities and using the same approach that we used for Tikhonov regularization, we can minimize the upper bound, and choosing k of the order of 1 over delta, we get that the duality gap is the Lagrangian gap is of the order of delta, and the feasibility gap again is of the order of delta, for instance, if delta is less than 1. So at the end, the iterative regularization approach is really comparable to the Tikhonov regularization one. And more than this, what is nice in these kind of results, even if they are still theoretical, they do not give an explicit practical rule to choose the stopping time k, is that in order to achieve these stability estimates, we have to stop our iterative method at the iteration, at an iteration which is proportional to 1 over delta. So if delta is big, we have a lot of noise, we stop earlier. If delta is small, it makes sense to go more on with the iterations of our algorithm. I want to mention that this kind of results have been proved also by Rush and Chambol in a more general setting, where you don't need the indicator function. So our contribution from the technical point of view has been to generalize this to the to the case also of the feasibility gap and to the preconditioning and inexact computation of the props in this strong sense. So here, for instance, we can have a computation of the props which never is noisy, and the noise never goes to 0, is over the order of delta. And we do not worsen the upper bounds except for a constant multiplied by delta. So as I was saying at the beginning, these are quite, in any case, not very strong results. The results can be strengthened in some special cases, for instance, in the case of sparse recovery. So the case where R is equal to the L1 norm. And then, let's say in this case, maybe the game is slightly different also for Tikhonov regularization. The goal is to find bounds of the distance between x star and xk delta involving only quantities depending on the sparsity level of the solution and not on the dimension of the space where the solution lives. And what we were able to derive are similar results, where here so we need to assume the RIP property. And under this RIP property, we are able to prove an upper bound which depends, as you can see here, on constants that depend on the sparsity level of the solution, and then the let's say the feasibility and Bregman distance. So with the I forgot a square here, I guess. So with the bounds that we have before, we can upper bound these two quantities, and we can derive an inequality like this. So here, the proof is based on some lemmas in the paper by Grassmayer, Scherzer, and Altmaier that did the same computations for the Tikhonov regularized solution. So when we compare the Tikhonov regularized approach with this iterative regularization approach, there are some differences in the constant that are worth to be highlighted. So the inequality in the constants for the Tikhonov regularization approach depend, as I was saying, on the sparsity level and on the true solution or the true datum V. Here instead, our constants depend also on the initialization of the algorithm. So in a sense, in this brings the dimension of the ambient space into play, and the noisy datum B delta. So this can be seen as a drawback of the iterative regularization approach, and indeed the upper bound is in a sense worst, qualitatively worst, but we have to think that when you need to find the solution of the Tikhonov regularized solution, probably you will use a forward-backward method, I don't know, proximal gradient algorithm, accelerated, whatever, and so these constants that are not there explicitly will appear again. So, and as you can see here, we have, as I was saying, if we are able to control both the feasibility and the Bregman distance, we are able to get strong convergence. So just in the last few minutes, I'd like to say that we are able to extend these results also to the unfeasible case. So the case where the system AX equal B does not have a solution. In this case, it is well known that the sequence generated by the Kondavu algorithm diverges. So it goes to plus infinity. And so it seems that there is no hope to prove convergence in this case, but this is not true. And we will see why. So the first idea is that if we replace the original problem by this problem P prime, very often the normal, so replacing the linear equation with the no associated normal equation, very often this problem has a solution. For instance, it is always the case in the finite dimensional case. And then the second observation, so the following observation could be, okay, now you have a solution that you have a problem that has a solution, just apply your algorithm to the problem P prime. But we didn't like this, since Landweber method applied to the original problem is able to adapt himself to the fact that the solution, the problem is unfeasible. You don't need to modify the algorithm. And so we wanted to prove the same result even for this more general algorithm. And indeed, this is true in the sense that if we assume that let's say a qualification condition, so a saddle point for this problem P prime exists, we can consider the average Kondavu algorithm applied to P, so to the original problem P. And then, so we have the algorithm that I discussed so far. And we can show that the primal iterates converge to a solution of this problem P prime. So the fact that this norm goes to plus infinity, it is due in these cases to the fact that yk goes to plus infinity, but xk is still converging to a solution of the problem that we want. And we can prove stability as applying the previous results. So we deal also with the unfeasible case. So in the 1 minute that it is left, I'd like to show you some experiments that are more examples, but just to check that our method was working on some references databases, benchmark databases. And in particular, so we tried this iterative regularization approach on the RCV1 dataset. And the purpose of this figure is to show you that basically iterative regularization and Tikhonov regularization does the same in terms of prediction errors, so of reconstruction. Here you can see more or less they are similar. In this case, in this example, we do not have access to the ground truth, but we have also other experiments where we use the ground truth in order to assess the validity of the method, the comparison between Tikhonov and iterative. And the take-home message here is that the iterative approach is much faster. So you see here, and we didn't cheat on this in the sense that Maturan Macias is an expert of L1 regularization, and he did all, they implemented all the tricks to make Tikhonov very efficient. So this is a true comparison. And another observation that came in a second time, just really trying to use iterative regularization with L1 norm, is the fact that we discovered while doing the experiments that a very relevant role is in the, for instance, for support recovery is played by the dual step size. So we have to say that compared to the Tikhonov trajectory, where you have the possibility of choosing the discretization and make it as fine, as refined as you like. For these iterative regularization methods, the trajectory that you build is discrete, and so sometimes it may be, I don't know, maybe not enough precise, not enough refined. Yes, and so let's say these if you want, the role of the discretization of the interval for the lambda parameter is displayed here by the dual step, and in particular we show that there are some choices that are empirical but satisfy the theoretical assumptions and can be that can be implemented, and for instance in this case guarantee a good support recovery. Otherwise, it can be that if you choose sigma too big, you become very soon non-sparse, dense, and instead if you choose a sigma too small, it takes a lot of time to reach the good support. And also we tested the impact of preconditioning. This is fine. It helps, as we already know, in the optimization, let's say, as we all know, I think, from the optimization point of view, this is very natural to expect. So, concluding remarks, the idea that the work that I presented today was about iterative regularization for inverse problems and learning problems. The idea is to develop regularization methods in which computations are tailored to the information that is contained in the data. The thing that I was saying before about delta, if delta is big, I need few iterations. If delta is small, I need more. And the proofs were based on an optimization point of view and are contained in this conference paper here. Enriched journal version, I hope it will be out soon. And the code that we use for the experiment is publicly available at this link. So next future work, we want to go towards the stochastic noise setting and maybe the learning setting, deep learning setting, nonlinear inverse problems. And so these are the possible directions. Thanks for your for the technical problems.
Silvia, for a very nice talk. You want to try, say, to switch on your video again? Let's see whether this works. Are there any questions, either from the audience or from the chat? Yes, Claire.
Thanks for the talk. So it's more a clarification. In your main theorem, what's your assumption on B delta is that the norm, the norm of the difference is controlled by delta? Yes, B delta minus B. Okay. And do you have extension where you don't control the difference with the L2 norm, but with another functional?
No, at the moment, no. For sure, it would be interesting. So we considered that kind of noise, for instance, in the paper where we had the diagonal approach for different data fits. So the distance between the noisy datum and the true datum was established using the data fit. That is maybe the most natural, the most natural idea. Until now, this is yeah. We can deal just with the norm difference, the norm of the difference.
Okay, thank you.
Thank you.
And also, but I think it's also clarification. Like in your algorithm, do you need to explicitly pass delta as a parameter?
No. So the idea, in principle, theoretically, yes. In principle, for instance, in the example that I was showing, we use the cross-validation approach.
Okay.
Okay, so you can use all the tricks that you use for choosing lambda.
Mm-hmm.
Any other questions? Yes.
So very nice talk, thank you. I wanted to ask a sort of a practical question, perhaps. When you say that the number of iterations has to be proportional to the delta, would it make sense to test out your problem on some sort of a really small scale to figure out what the proportionality is?
Yeah. So yes, at the certain point, I think we tried, yes, but we don't have a quantitative answer. So we know, so theoretically, yes, in the sense that I didn't write all the constants here because I didn't want to be to add too much notation, but we more or less know what are these constants here. So I start from here because I remember and it's easy. This is, for instance, this depends on the initialization of the algorithm, the Lipschitz constant of the smooth part, for instance, the norm of A. And then you have terms instead which take into account, for instance, the error in the prox or the, and instead terms that are difficult. So it depends on the step size, of course, but are difficult to estimate from an explicit point of view. Yeah, it would be, yeah, we should do this experiment seriously at a certain point. I agree.
As we are on this slide, Silvia, I've got a quick question. Is that a type of this 1 plus delta at the bottom right?
Yeah.
Should this be there? This like that the feasibility is bounded by C delta 1 plus delta?
Delta. Yes, it's delta plus delta square. So if delta is more than 1, it's delta.
Okay. Yeah. Okay. Yeah. Fair enough.
Yeah.
One final question by Martin.
Hi, Silvia. Thank you very much for the very nice talk. One quick question. You have this example of where you showed that the Bregman distance itself isn't obviously as much of a strong error measure as the one norm on some slide or some other norm. One thing I was wondering, because obviously if the Bregman distance turns 0, then at least the support and the signs should be correct.
Yes, exactly.
Do you have an idea of what happens algorithmically with the conduct algorithm? Why this sort of like seems to shoot back and forth, and then also, but in norm doesn't never really solve it on the support?
No, I don't. So yes, so I agree with you. Is exactly as you said. Basically, you can have Bregman divergence equal to 0. So you have Bregman distance equal to 0 every time that xk and x star have the same sign support. So this is what the Bregman distance tells us. And yes, I don't know exactly what happens with the primal-dual. We observe very, very weird behaviors, even in examples in R2. And yeah.
Interesting. Yeah, interesting.
I don't know what to say more than this. And also, this behavior is really governed by the dual step size. So we observe that the dual step size has a very strong impact. And I think this is in a sense correct in the sense that there is a paper recently came out, I think 2 days ago, on arXiv by Francisco Aragon Artacho and other co-authors, and they observed, so they did exactly an experiment on the role of the dual step size in convergence of some kind of primal-dual algorithms. So, and this is related to this oscillating behavior you were mentioning. But I don't have more insights than this.
Well, thank you. Yeah, it's definitely interesting. I'd be curious to understand this more. Yeah, thank you.
Thank you.
So I think we are a little bit over time. I think it's time for like a tea break here in Cambridge. So thank you, Silvia, very much again.
To you, thanks very much.
Now it's time for tea and coffee, and then we reconvene at 11 a.m. UK time.
See you later.
Lots of the next speaker. Can I quickly test?
Nice. Finally. Cool.
I'm really sorry about this.
No worries at all. No worries at all. So then, welcome back, everyone. Let's make a quick start. So our next speaker is Silvia Villa, and so she's a PhD student at Paris Università, MAP 5, and supervised by Sylvain Durand, and she will talk about inversion of integral method models. Stage is yours.
Okay. Okay. So hi everyone. So I will present a work that I have done with Émilie Chouznou and Jean-Christophe Pesquet on inversion of integrals models using a neural network, and more specifically, I'm going to focus on Abel integral. So first, I will present the biophysical model that leads to inverting an Abel integral. I will present one model. There are several inverse problems where such operators arises, but here I present only one. Then I present a motivation for our inversion strategy. Then I describe more precisely the method, combining variational approaches and neural network approaches. Then I present the architecture of the neural network. I will discuss stability theoretical result and illustrate this result with numerical experiment. So first, in aggregation phenomenon, you have a cluster of size I containing C particles. And for example, if you have a filament of particle at its end, you can add or retrieve a particle. And you have two types of chemical reaction. So if we put that in a mathematical setting, we have the Lifshitz-Lozow equation. So if U is a concentration of a cluster of size X or I at time t, then its concentration satisfies this equation, which is a transport equation of the speed at any time tau. Here you have the initial condition that I denoted minus X, and the last line accounts for the mass conservation in the system. So I just rewrite this equation with the V, the speed of the reaction. And I suppose that I have access to V by another mean. And so now the type of measurement that I can have in such experiment is a moment of order A of the solution U. So a moment can be defined as follows. So it's an integral over the minimum size of the system and the maximum size of the cluster of X power A, the size power A, times U. And now U is linked to its initial function with the characteristic method, since we have a transport equation. Now, by a change of variable, I can rewrite it as an operator acting on X, the initial signal. So my inverse problem is reconstructing U, or equivalently X, from a measurement Tx. So T is now an operator from L2 to L2. This operator is in fact a type of Abel integral. So I redefine the Abel integral T minus A X, which is an integral on 0 to T minus S power I minus 1. And I had a kernel here that allows us to account for a larger variety of biophysical model times X. This operator is well defined from L2 to L2 as long as K is an operator from L2 to L2 and X is also, of course. So K is L2 from omega to omega. So now the measurement that I have is Y, which is the image of X. Yeah, hello?
No. Camina down.
Okay.
Camina. Camina. Coffee, beer, Camina.
Yeah, sorry. And we don't have access to Y, but yeah. So sorry. So we don't have access to Y. We have access to Y delta actually, which is a noisy measurement. So the level of the noise is denoted by delta. So here we want to, our inverse problem is to invert TA. So we're constructing X from a noisy measurement Y delta. So this is so why is it ill-posed? So if A is equal to 1, we only have the integral operator. And so the inverse of T1 is just a derivation. But since we have access to Y delta, which is in L2, we have to make sense of the derivation of Y delta, which is not possible. So more generally, all the TA operators are compact and their inverse is not continuous. So one strategy to gain this continuity is to add a regularization term, so to use, sorry, a variational method, which is a minimization on a feasible set denoted by C of a data fitting term and a regularization term. So this approach incorporates prior knowledge about solution and enforce desirable constraint and is grounded on clear mathematical concepts, but it has drawbacks. We don't have closed form solutions, so we have to use iterative algorithm. The objective function not always reflect the perceived quality, and estimation of the regularization parameter and the algorithm parameter is time consuming. It is only done by the experimenter during experiment, and sometimes we don't have general rules to set these parameters. So on the other hand, in deep learning methods, we have generic method for linear approximation. It's an efficient way for incorporating prior knowledge from big database, which can account for this perceived quality. And drawbacks, it makes it difficult to account for physical models, and it's the black box. So to combine the benefits of both approaches, we suggest here to unfold optimization algorithm. By unfolding optimization algorithm, what I mean is that instead of iterating an algorithm till convergence or till how we define the convergence, I only unfold the optimization algorithm over a defined number of iterates, and I can plug a neural network in these iterations. So first I define the progressive gradient descent. So if we take only the basic optimization problem, X belongs to a feasible set, we want to minimize this data fitting term. So one way to do that is the projecting gradient algorithm. So at each iteration, I project on C a gradient descent step of this twice differentiable function. Okay. So now if I rewrite the projected gradient algorithm, I can rewrite it as a linear part applied to Xn and a bias. The linear part depends on the gradient step, the operator, and the bias depends on the measured solution. So now we have almost a feed-forward network. It looks like it because here, instead of a projection, in a feed-forward network, we have an activation function. So I define G, my neural network, which is a combination of linear operator, the sum with the bias, and an activation function. So G is a layer of my neural network. And Wn can be, for example, convolutive operators. So now I still have to make a link between my projection and my activation function. So I define the proximity operator with a set of proper lower semi-condition convex function. The proximity operator, proxg, is the argmin of over Hilbert space of G plus 1 to 2 the norm of z minus x. The special case for an indicator function of a set, then the proximity operator is exactly the projection. So we have a link from the projected gradient algorithm to the forward-backward algorithm. And what I assert here is that most of the activation operators are in fact proximity operators. I will give 2 examples. For example, ReLU is the projection on the set 0 plus infinity, but also parametric rectified linear unique ReLU. The prox is it is actually the proximal operator of this function phi. Softmax is also a proximity operator, and this type of computation can be done with a very large variety of activation functions. So our method, let's go back to our problem. I made an assumption to assert that there is a solution to our problem. So I defined the problem P0 to minimize, it's still the same problem, on a feasible set, a data fitting term, and a regularization term. I assume that both terms are twice differentiable, and the sum is either coercive or C is bounded. I define the feasible set as a finite number of conditions, and I said that the interior of the feasible set is not empty. So that provides the existence of a solution to P0. And the twice differentiability is important because in training, we're using stochastic gradient descent, and that is a good property. Okay, so now my constraint problem. So if I imagine that I have a feasible set in between those 2 lines, and this is my function, what I say is that with a projected gradient descent, the projection is not twice differentiable, and we have vanishing gradient issues during training. So that is why we prefer to solve an unconstrained subproblem. I define the logarithmic barrier of my constraint, and instead of minimizing over a subset, I minimize on the whole space, and I had this term, that is this function, and you see that it transforms my function to minimize and constrain it to be plus infinity outside of my feasible set. So now P0, my problem, is replaced by a subsequence of subproblem P mu, and with the sequence mu tending to 0, I find back the solution of P0. And now the main advantage is that I have feasible iterators. So to solve such a problem, I have the interior point method. I can define my iterates as the proximity operator of my function, but I don't have closed form expression for this proximity operator. So what I do is I come back the forward-backward proximal interior point method. So I do a gradient descent on the differentiable part, and I only compute the proximity operator of the barrier. So now I have rewrite my algorithm, but I still didn't plug any neural network. So the question that I have now that I have my algorithm is how do I set the parameter, the barrier parameter, and the gradient descent parameter, and I still don't have find the regularization parameter leading to the best quality of the solution. So now I unfold my proximal algorithm over m iteration, and I untie the parameter across the network. So if I define one layer or one block as this operator, I have two inputs, x0 and b0. B0 is linked to the measurement. My neural network is the combination of m block, and in each block I have my operator A, that is my activation function, my proximity operator, the linear part, the bias that is always the same, and all the parameters are computed with neural network. So in my hidden structure, I have one neural network that estimates the step size, one neural network that estimates the barrier parameter, one neural network that estimates regularization parameter, and each are repeated in each block. So, and then in my block structure, I compute this operation that looks like a feed-forward network. So I will describe all the neural network. So to estimate the step size, since the step only depends on the structure of the network, it doesn't depend on the initial solution or initial input or output. I only learn and enforce positivity with the soft plus. So I only learn a scalar. For the barrier parameter, I have two types of constraints that I want to apply. So first, an affine constraint. For my cluster problem, for example, it would mean that the size of a cluster is bounded with two size limit, or hyperslab, which is a bit more tricky. But for example, the mass of the system is the moment of order 1 of my solution, and what I can say is that initially I want to ensure that the mass of the cluster doesn't exceed the total mass of the system. So that would be hyperslab condition. And so the barrier parameter is computed starting from the input of on a block. I do two average pooling and soft plus, and then a fully connected layer plus soft plus. There is, this is experience-based and it works well. And finally, for the regularization parameter, since we choose a regularization that is of the generative enough type, we have literature that gives up to a constant a theoretical optimal regularization parameter. So I use this formula, and I learn the scalar D in front of the formula. So now, what about the stability of this network? Well, just to recall, there are a lot of issues around stability of network. In deep learning, we know that generally we have a lack of robustness in most classical neural network. And there are a lot of applications with high risk so there is a need for theoretical guarantees and not only experimental guarantees. So a work has been done before on the stability of this type of neural network, and the stability has been computed to perturbation of the input x0. What I had is that I compute a stability to a perturbation of the observed data y delta, which is linked to the bias. So it's almost like computing here the stability of a feed-forward network, and here our residual neural network. So first, I recall what is an average operator, which is a good tool to compute the stability of asymptotic neural networks. So if G is my neural network from a nilbelt space to a nilbelt space, G is alpha average if there exists a non-expansive operator R, such that G equal 1 minus alpha identity plus alpha R. So if G is average, it is non-expansive. And if it's average, it respects this type of inequality, and in particular, the output of G is bounded by the input. So I show you here a theoretical result from Combet and Pesquet that we're going to use. We used in our work. If we define W as the combination position of all the linear parts, and we define theta minus m minus 1 as the sum of the norm of a combination of W, then I can say that the neural network G, I can exhibit a Lipschitz constant. And I can also say that if this inequality is met, then G is alpha average. So just to show you, what does it do? If M is 2, that means that I have only 2 layers. Then theta 1 is this formula, and theta 1 2 is the Lipschitz constant of G, and the inequality gives us this. So up for a 3-block neural network or 3-layer neural network, the computation is a bit more difficult, but I still can exhibit a Lipschitz constant and a condition for alpha averageness. So the take-home message is that the stability of a neural network depends on its weight operator and not on its activation function. And I have a rule for computing a Lipschitz constant. Even if it's a bit complicated, I still have a rule. So this theorem has been done in a feed-forward architecture. But I don't have exactly a feed-forward architecture. Here, I want to compute the stability on the bias operator, not only on the input. And so to do that, we define a virtual network, which takes as the input Z, which is X and B. And now the activation function is in a larger space of L2 times L2 with one input has the activation function and the other one is the identity. And so now I have to define the norm of a virtual network, and I take a norm on L2. Okay, so now I have the rule to compute my theta, and I have the norm to compute it. So I do all the computation. I still have one assumption that I need to do this computation. I assume that T star T and D, which is a regularization, it's a derivative, are diagonalizable in the same basis. And so I can compute eigenvalues in the same eigenspace. And so I just show you the computation, but I will not detail it. It's just that we can define and compute exactly those 2 terms. And then thanks to those 2 terms, I can define the norm of U, which would be like this. And I have studied 2 subcases. If the input is 0 and if the input is equal to B0. So if the input is the measured data. And so now I have a rule also to compute the Lipschitz constant of my neural network, which is linked to the eigenvalues of my two operators. Okay, so now I show you, now that I have a rule to compute my Lipschitz constant, I'm going to apply it to a real neural network. So first, there does not exist a large data set as it does for image for 1D signal of cluster. So we have to build a data set that is coherent with the observation. So obtain a large variety of bimodal or quasi-bimodal signals with variable peak width. So I exhibit, for example, 3 signals that I have, construct. And here I show what types of signal we can measure. So here is a perfect image, and here is a noisy signal for a equal 1. So this is only the integral, and then for a equal 0.5. So for the training, I have 330 signals distributed as follow: 200 for the training set, 100 for the validation set, and 30 for the testing set. I have 4 test configuration: a equal 1 and a equal 0.5, and I have also my affine and hyperslab constraint. I train the neural network end-to-end fashion. My love is MSE. I use PyTorch. And this is the kind of, after training, the kind of output result that I have. So I made 3 remarks. The output errors are low when I compute them. The output signals are smoother than the expected signal. And when I equal 0.5, it gives a better output, which is coherent with this consistent, with the theory, because the problem is less ill-posed when a equal 0.5. And I also have, I can compute now a Lipschitz constant in the 4 subcases that I studied. So what I can say is that the Lipschitz constant do not vary much, neither according to the choice of a nor of the constraint. And also the constants are lower than 1, even very low. And the algorithm tends to constrict the solutions. This can be explained because the space of solution is smaller than the space of the input. So to conclude, neural network architecture built in an is built in an explainable manner. Sorry. We show an efficient method developed by mixing ideas from iterative optimization or variable algorithm and neural network techniques. We also have an expression of the proximity operator of the barrier function and their gradient. I didn't show that, but that's what has been done in this work. There are requirements of better non-convex optimization methods. Optimization concepts are not only useful to train neural networks, but also to analyze them, as I shown with Lipschitz constant and alpha average methods. This is related to competition. Thank you for your attention.
Thank you very much, Lucy, for a very nice talk. We have a lot of time for questions. Are there any questions either from the physical or the virtual audience? Yes, Claire?
So in in the stability part, you have this requirement that two operators need to be jointly diagonalizable. How practical is it? I mean, how do you deal with this assumption in practice? Does it constrain a lot your applications or not?
For the case of the Abel transform, there has work that construct the basis for D and for T. So for the two, and I mean, it's a case-by-case based problem, depending on your operator and the regularization operator that you choose. It might be difficult to have the diagonalization is the same basis. It means that the two operator commutes.
Yeah.
Well, it was a case in our application, but it can be also a limit to this method. Don't know if that answers your question.
It does.
Any further questions?
So it was a really nice talk. Could you please remind me, how did you estimate the step size? So you said that you had a separate network to estimate step size.
The step size, yes, it's just a scalar that is learned. There is no input.
Okay, because you were saying earlier that the step size only depends on the network architecture, rather than any sort of input. I was just curious, how was it learned, considering it depends on the network architecture? I didn't quite get the connection.
Okay. In our neural network, we have a parameter that is used through the network, and we backpropagate on this. But the scalar is learned. I mean, I think so. Okay. Okay, so here the output will depend on the scalar, and I say I just learned the scalar. So it depends on the input, because when I compute A, I backpropagate here, but there is no other hidden structure for the gradient step.
Yes, so you learn it through backpropagation.
Yeah, just here. That's it.
Any other questions? Okay.
Yeah. Like, more generally, like in your last slide about the outlook, you say that you need more progress on algorithm for convex, not necessarily strictly convex algorithm. Can you explain more precisely what you would need in order to? I mean, what are you looking for?
What am I looking for convex? Well, I was actually I was thinking of the Chamble-Pock method. But Sorry.
We can also discuss it offline.
Yeah, sorry.
Thank you.
It looks like I think there are no more questions from the audience virtually. Is there anything? No, right? Then let's thank Cecile again.
Thank you.
It's time for a small break and then we reconvene at 10 to 12 UK time. So, should we get going? You ready? Yeah. Fantastic. So now it's time for the final talk of this morning's session. And so the final speaker is Martin Benning. So he did his PhD at the University of Münster in 2011, and then has seen like various places, Cambridge and Lübeck, before then moving to London to Queen Mary University in 2018. Mm-hmm. And he recently got promoted, and he's now the participant, I would say, with the most fitting job title to this workshop. He's now a senior lecturer in machine learning and inverse problems, so therefore like perfect fit. So here's Martin.
Thank you, Matthias. And I'll probably give the least fitting talk because inverse problems today will be, unfortunately, a bit of a side note, but I will tell you at the end what I'm actually. Well, this is sort of just the first step towards something that will definitely involve more practical inverse problems. But yeah, thank you very much for the kind introduction. Thank you very much for having me here. Also to all the organizers for actually a great program, and also actually definitely to see more physical participants again. So I hope I will do it justice in trying to address both the physical and virtual audience. So first thing I want to say is this is joint work with my PhD student Victor, who's actually also in the audience. So I will direct all the questions discreetly to him afterwards. No, I'm joking. And the talk is, so the outline of my talk is I will first try to give a bit of overview of alternative strategies. So mostly what this talks about is different strategies of training neural networks as opposed to our classical, let's use a gradient-based approach for spectrum propagation. And then I will describe the approach that we pursue or want to pursue, and has a few advantages as opposed to some traditional approaches. We'll also briefly discuss how this formulation that I'm going to introduce or develop, how we can optimize this, and then conclude with a few very preliminary numerical results, and conclude with conclusions and all. Okay, let's get started. So I want to talk a little bit about distributed optimization, so to train neural networks, or for the training of neural networks. And just so that we're all on the same page, I introduce some notation, which you basically all know. Everyone here knows what a neural network is, but I just want to introduce it anyway. So an L-layer neural network is a composition of parameterized functions. So we denote them here as F. They could obviously all be different, these functions F, notation-wise, or just keep the same notation for notational simplicity, but they're all take an input, but they're all also parameterized with some parameters theta, and the parameters obviously in the neural network, they usually vary. And so training of neural networks, we also know, normally usually boils down to some minimization or approximate minimization of empirical risks in almost all forms. So where we formulate some particular energy, in this case here, some loss function L that I don't really specify, give an example in a second, but we already can think of square 2 norms or other terms. And we're trying to somehow minimize this, and not really just minimize this, but also hope that it works well on unseen data. So minimize the validation error, but I'm not really going to address this too much in this talk today. So yeah, an example for loss function is to have something like a square 2 norm, and then for a neural network architecture, popular having affine linear transformations surrounded by activation functions sigma, for instance, rectifier or hyperbolic tangent, so that we get in the rectifier case something like a rectifier linear unit. Yeah, we have seen this also in the previous talks. This would then constitute a feed-forward network, and yeah, in the majority of cases, so as I said, the minimization is normally carried out by a combination of 2 things. Having something like a gradient-based optimization, that would be, I don't know, stochastic gradient descent, or anything with like any variant with acceleration, like Nestorov acceleration, or so you name it. You can have Adam W, all these algorithms that are out there, and then they all require, to some extent, to compute a gradient or partial gradient, and that is usually or often being done with backpropagation, basically evaluating the chain rule in some specific order. And today, so the idea, or well, actually one example before I say what's the idea, the talk is, so if you had like the objective from before, and let's say you were to use gradient descent, then obviously we would just have these gradient descent update formulas, and the gradient we would evaluate with backpropagation. I spare you the formulas, because obviously with automatic differentiation these days, this is all being done pretty much automatically. But so there are potential drawbacks of this classical approach, and that on the one hand, computing gradients requires, in this case, of the differentiation of the activation function, which in practice often people don't really care about, do it anyways. Even let's say if we have the rectifier, the ReLU type rectifier, if it's not differentiable, and just take a subgradient, and in practice it usually works fine. There are also theoretical justifications why it's unlikely that you hit artificial critical points. But the other thing is that in general, with the structure of this iterative structure of doing a forward pass and backward pass, it's quite difficult to parallelize the backpropagation approach, which, yeah, is one of sort of the key reasons why I'm doing this talk today, to basically walk you a little bit through sort of different paradigms in terms of the optimization. And for simplicity, I will now assume that the loss function is always the squared Euclidean norm, but you could also adopt other loss functions. But I don't want to throw too much notation at you, so that's why I'm going to stick to squared 2 norms. Okay, so we want to look at alternative approaches for finding these parameters. And I skipped the notation with having multiple data samples. We just stick to one, but obviously in practice we would have more than just one set of pairs. And so a very simplistic approach, and I'll also give you a reference in a second, where I'm always wondering if there aren't earlier works that were doing something very similar, is to introduce auxiliary variables. So basically for every hidden layer, for every evaluation, we introduce like an extra variable xj. And notation wise, I say that the very first one, so the x0 is my input x, and the very last one, XL, is my output Y. And what we can then do, and this is normally, at least in literature, is usually accredited to this paper by Carrera, Perpinan, and Wang on distributed optimization of deeply nested systems. Again, because the idea seems so simple, I'm wondering if there is sort of earlier literature. Is basically now say, okay, instead of just minimizing sort of the objective for the final sort of output of the final layer, we create like a new objective where we basically look at the difference between all these individual variables, new variables x, xj, and we sort of minimize the loss function. And in this case, as I said, I'll just stick to square 2 norms for now. And we minimize this instead. And we, as you see here, we basically introduce these as new variables. So we expand the objective by introducing new auxiliary variables, but we also have to optimize for them. Yeah? They're not like given, we have to compute them. But one thing that is sort of nice about this formulation is, because you would think like, wait, hold on, you've changed the objective, so does it actually make sense to solve this? You still solve the same problem. And if you look at the optimality condition with respect to your parameters, the nice thing is, if we were now to assume that the gradient with respect to the parameters of that activation function at sort of layer xj minus 1 were like not 0. Obviously, we have no guarantees for this at this stage. But the nice thing is then that we can basically ensure it from the optimality, obviously in the limit when we have solved this optimization problem, that we actually satisfy this sort of constraint that xj has to be equal to f of xj minus 1 of theta j. Because otherwise, obviously, you wouldn't really solve the same problem. And to be fair, obviously, numerically, solving this really to such a precision that these optimality conditions are really 0. It's obviously a different matter, but we're going to get to this later. But this is basically sort of the approach. And it has been, and the nice thing about it, I should have mentioned this, is that if you now want to employ an algorithm and you have these basically all these additional variables, the nice thing about it is that you can parallelize this quite easily, or even distribute it quite easily. So you can try to employ algorithmic strategies that optimize these sort of individually, and then basically merge the results again and distribute it again, and so on and so forth. And this is the main motivation of this paper here. This was basically their angle of where they came from. And they also show that, you can successfully sort of train a network. For this talk, this is not so much my focus. My focus is more about the limitations of these approaches. And so one thing is that what we have to do here is we still have to differentiate activation functions. That's one thing. No, wait, that's the main thing. No, there's not more coming with the main thing. So, and just again, as a reminder, if you have obviously popular activation functions where you have a ReLU, then technically there isn't actually really a single differential, so you have to have subgradients, so your algorithms all become subgradient-based algorithms, and it may not be the most desirable thing. So then there was some other work that tried to address this issue, in particular for the case of rectified linear units. That's why I highlighted them here. And this is where sort of this terminology of lifted networks comes from. So if we go back to the previous approach, this Carrera, Perpinan, and Wang approach, then basically would have an optimization problem where we plug in this on the activation function. So it's very similar to like the original problem, just that we introduce these additional variables, and we don't really overcome the issues that like we have to differentiate the max function. There's definitely a kink in the function, so it doesn't really change this. So what had been proposed as an alternative, and this is going back to some pointer here to this paper by Ascari et al., which also coined the terminology of lifted neural networks, is to say, okay, how about in the particular case of rectified linear units, why don't we get rid of this rectifier function, but instead we ensure that our sort of new intermediate variables are non-negative with a constraint. So instead of trying to solve the original problem, now replace it with a constraint optimization problem, which overall is still a non-convex problem because you have these multiplications of the parameters. But it does have a couple of nice properties, especially that if you keep variables fixed, you suddenly end up with convex subproblems. If you do some form, for instance, coordinate descent or alternating optimization, you end up with convex subproblems, which is quite nice. And also you end up with, you still in a somewhat easy parallelizable or distributable regime. But, and you also, for everyone else, obviously, you've also seen in the previous talk projections, and basically end up with quite easy to compute updates depending on what algorithm you use. But obviously, if you use anything proximal based or projected coordinate descent based, then you get something that is quite easy to compute in many ways. But there's a huge catch with this approach. Of course, of the not so nice property is that what you train here is very different from the original problem, because you effectively train an affine linear network. You don't train a neural network anymore where the affine linear transformations are followed by nonlinear activation functions, but instead you ensure that every one of those affine linear transformations is actually non-negative. And so is the first one, and then so is the next one. So basically ensure this for all of them. And yeah, this is obviously not the same as solving like the classical sort of ReLU feed-forward network. So it's more restrictive because you don't have the same degrees of freedom, because obviously in the bottom case, I can have transformations that map things into something that's negative, which is then being cut off by the rectifier. Whereas in the first case, we try to really avoid this, to just learn transformations so that this doesn't happen. So what my sort of key take-home message of this talk is I want to go away from, basically I want to build up on this previous approach, but we want to change the formulation so that we overcome these limitations that we've just seen. And this, in the analogy of lifted networks, we coin this lifted Bregman networks because, surprise, surprise, as you're going to see soon, there will be some Bregman distances involved. And everyone who knows me knows that that's basically my sort of academic career based on Bregman distances. Just kidding. But so coming from that lifted feed-forward neural network representation that we've seen, so we basically just want to make one simple change, or maybe not so simple. We are actually going to replace this sort of particular distance term here, the squared 2 norm, and we also get rid of the sort of constraint set. But the key thing here really is to say, okay, we have also in the Carrera, Pepinan, in one paper, we have this distance here, squared 2 norm, between our new variables and this activation function and defining the transformation, or in this case with the constraint. And what we do is we're actually going to replace this with something that's actually more suitable or gives us sort of advantages as opposed to this approach. And this is something that's unfortunately still work in progress, but it shouldn't take much longer until it's much of the writing is done. So hopefully it goes into archive very soon, which is the sort of lifted Bregman network approach, where we replace this squared 2 norm here with a new function. We term it like a Bregman loss, which also consists of the squared 2 norm with sort of our activation function. I'm going to actually explain the notation in a bit. So this L function, I'm also explaining what this is going to mean. So don't worry, I'm going to walk you through all these bits. But so the key thing here is really we replace this with a different sort of distance function here. And the distance function looks like this. And we'll have the following advantages. So before I introduce this, what all terms mean, I'm going to basically show you the optimality system, optimality conditions for the parameters of wj and vj, because what I'm going to walk you through in a bit is that when you compute the gradient with respect to the parameters, and for instance, with respect to the parameters w, what we get is basically the condition that if we ignore the xj minus 1 for a moment, or if we say go to the optimality condition for bj, is that we have, in terms of optimality, that we will satisfy this condition that the hidden variable xj equals the activation function of wj times xj minus 1 plus bj. So exactly the sort of neural network condition that we want by introducing these new variables. And this time, we don't have just a affine linear transformation where we enforce some non-negativity of the outcome. No, we actually have an activation function. This is sigma, going to be activation function that we apply to this affine linear transformation. So we get in principle the same as before, but now in the sort of correct way with the activation function. But the key thing is obviously now, hold on, where did you come? What is this distance term? Where it's all coming from, and how do you actually prove this? And that's what I'm actually now going to do for the next couple of slides. Also, work the time a little bit. So this function here. So now I'm starting to explain the different terms. So this L function here. So I'll replace this argument now with the simpler argument Z, and this with the Y. So when we look at this distance term here, it's basically just a square 2 norm of which would normally be in the Carrera piping and one paper. This would be the actual data term that we use with, for instance, here like a rectifier inside, whereas we add something to it, which is a generalized Bregman distance with respect to a proper convex and lower semi-continuous function psi. I'm going to give some examples in a minute between the same arguments and for a particular subgradient. So the Bregman distance is the difference between the function and its linearization around a particular subgradient. So it's in this case for this subgradient, this particular expression. And just to give a few examples for those who haven't seen Bregman distances before, or Bregman divergences, they're usually called in statistics, is so in general, when you have two arguments in function, it's really just this difference at some subgradient QV. If psi is differentiable, you can think of this as just a derivative of psi. And to give examples, if you have something like square 2 norm, Bregman distance, just a square difference of the arguments. If you have something like the negative log entropy, you get something like the Kullback-Leibler divergence. And one thing also I haven't really mentioned in terms of notation. So what is sigma here? I have already said it. It's an activation function, but we now restrict ourselves to very particular activation functions. And we have actually seen that in the previous talk as well, which was quite nice. I almost skipped the introduction here, is that where in the previous talk also proximal maps have been used as activation functions. And this is exactly what we do here. And this is how the notation comes together with this function psi. So we assume that sigma is exactly the proximal map with respect to a function psi. And this may seem restrictive at first for activation functions to specify or to choose particular classes, but we have actually seen in the previous talk already that lots of conventional activation functions are proximal maps. And here I have a couple of examples as well. So we saw this in the previous talk that we have when we have the characteristic, so the characteristic function on the non-negative orphan, we can actually get the rectifier function again. But we can have things like soft thresholding if we choose the multiple of the modulus. But we can also construct like continuous functions like the hyperbolic tangent, which then results in a bit more of a complicated function psi, but we can basically characterize them as a proximal map. So it's actually quite a large set of useful functions, activation functions that we can use. But coming back to sort of these the distance term that I constructed. So the first thing I want to clarify is this particular element here, is this actually really a subgradient that I can use? And now that I have introduced the proximal map, we can actually quite easily verify that, so that z minus sigma z is in the subdifferential of psi at sigma of z, because this is just the optimality condition of the proximal map. So this is actually how I chose the subgradient. And yeah, before I start to actually prove the statements that I've shown you earlier, I want to also show you an example. So what does this Bregman loss function effectively look like if you compare it to your normal loss function? For example, if you take, let's say, the squared 2 norm between your rectifier function and some output and what the Bregman loss function is. So we see in red here, the dashed line, this is your original objective. And here we see sort of the kink and the non-differentiability that ends up. And what this loss function now basically does is it sort of continuously extends it in a meaningful way, and in a way that gives us sort of the gradients later on that we're interested in. And yeah, in this particular example, the function can be simplified to this particular expression. So sorry, I should have written the max here as well. It's a bit of a notation fail. But yeah, but you can also, for other activation functions where it's a bit more complicated or not as easy to see, you can do the same thing and get something like that. Avoids the non-differentiability if it exists. And so what we now still have to do in the last sort of couple of minutes is to verify what I said earlier. So because the main take-home message was that we now really have a lifted formulation where the optimality system gives us the neural network that we actually want. And for this, I've stated it and stated what I now give you as a theorem. So when y is in the domain of psi, the gradient of this function with respect to z is simply the activation function of z minus y. Or if you put it back into the constant of our lifted networks, if you compute sort of, if you have the finite transformation in this, you get the basically optimality system that I just wrote down earlier. And the proof for this is actually much simpler than you may look at first. It basically just involves the Moreau-Uzida regularization. And here I apologize a little bit that I suddenly used EZ for the Moreau-Uzida regularization. That was a bit of a bad choice because I used E before. With a few changes for future talks. But so what we first look is we look at the Moreau-Uzida regularization, which is basically the function, and you plug in the proximal map. That's a smoothing of your function psi. And what we then observe is if we go back to our functions, we can actually write it in terms of this objective EZ. And that's what we basically quickly do. So if I write down the definition of the Bregman distance, and if I do some very basic sort of arithmetic sort of changes for algebraic manipulations. So for instance, writing the squared 2 norm as the inner product of itself and then splitting, moving this inner product here and combining these. And also in the interest of time, I think I moved through this a bit quicker. So those who have seen my extended talk, they already know this part anyways, and obviously I will upload the slides. So we basically just do a few manipulations quite simplistically to arrive at following function here. So we can basically rewrite it as this sort of EZ of y. And this is the Moreau-Uzida regularization. So here, what we introduced earlier, so we have this function EZ where we plug in y, and then here where we plug in the proximal map. And so why do we do this? Because the well-known fact about the Moreau-Uzida regularization is that the gradient satisfies that when we take the gradient that we have z minus sigma of z, or equivalently the proximal map of the dual function of psi. And so if we use this in this particular, if we now compute the gradient with z of this overall formulation, then we simply get sort of z minus y from the objective ez, and then we get the gradient z minus sigma z with a minus, the signs change, and we basically end up with sigma of z minus y. So it's really just the more easy regularization above anything. But yeah, it gives us an energy that when we take the gradient, we do not have to differentiate the activation function. So that's actually, I would say, quite a cool thing, quite an interesting thing. And a small summary. How I'm doing time? I should
do quite well, like 12 minutes.
Oh, okay. That's good. Thanks. So a small summary of this particular energy, because I think it's actually the energy is probably the key thing of the whole approach. Is so there are some drawbacks in the sense that it isn't like a metric anymore, as for instance using like a norm. But the nice thing is that it is sort of an upper bound for your quadratic energy that you would maybe normally use. And you obtain obviously a global minimum when those arguments equal. The function is sort of biconvex, so it's convex in each argument in itself. Also, when you think about alternating minimization, that's quite a nice feature. Obviously, I mean, this is more like a trivial fact. It comes from the activation function, but also gradients obviously are monotone of convex function. Sorry, this is the other way around. Right? So when it's biconvex, then obviously the gradient is also monotone, but the monotonicity also comes from the fact that proximal maps are monotone. But also the gradient is one Lipschitz, which is also quite a nice thing because it's basically just the activation function. And proximal maps, sorry, it's just a proximal map, and proximal maps are one Lipschitz. And one important thing just to bear in mind that comes from for the numerical optimization is we can rewrite the objective since it's a Bregman distance. Since the first part is actually also Bregman distance, we can write it in into like a combined Bregman distance, and then for everyone who knows Bregman distance is a bit better and the relation to conjugates, we can even separate it into this part where we have something that depends on y, then the conjugate that depends on sigma z, and then just an inner product between y and z. So that's actually quite nice because later on we can, when we do like alternating optimization, we can actually really split these parts and use something like proximal methods to approach this object. Okay, so one conclusion. So we have basically all we proposed here is to say we have this sort of lifted approach, but we exchange the squared two norms in the approach with different function, the sort of Bregman loss function, so that we get a more natural, a better optimality system that also doesn't require us to differentiate activation functions. And as it is always with things like this, when you hope that you're the first one to do anything like this, then you suddenly realize there are other works that go in very similar directions. Although we have some advantages over those papers, is that they have similar approaches where they, however, require strict monotonicity of sigma, which rules out, for example, the rectifier function, which is just monotone, and some other sort of theoretical limitations. But effectively, those approaches are very similar. Therefore, I want to mention them here for completion. Okay, I want to use the last couple of minutes to quickly just say how can we optimize this, because it's maybe not as straightforward, and how do we also optimize it so that we gain something, or we can do something like distributed computing. So the question would really be how to minimize this objective, and obviously you can technically, if you want to, you can just throw everything at it in the same way and just ignore like the nicer structure. But we want to focus particularly on basically proximal coordinate descent. So if we look at this particular objective from this characterization that I've shown you earlier with this sort of conjugate, we can actually separate this objective into a function which basically just depends on these new variables xj, and then a differentiable function that depends on all the, so it's its first part, it's like a non-smooth function that just depends on xj, and the other part depends on all the variables, but in a smooth way, where we can compute the gradients. And so we can write the overall objective in a separable way. And therefore, we can then use proximal coordinate descent, for example, where we just use gradient steps in a coordinate, points in the coordinate way. And here also, we could technically, we don't have to do it sequentially. If you're interested in distributed programming, we obviously can do it in parallel. And therefore, we still have this sort of nice parallel structure. Do gradient updates, have a proximal update, and that's basically it. And the proximal update is just depends on the side. So we have that we use that proximal mapping anyway, so it's actually relatively straightforward. And I want to basically conclude with a few preliminary results. So the first thing that we did, and this was actually that we have a preprint, or not preprint, we have a conference paper for this. That was actually how we initially started with just one layer, and to actually see how we can actually characterize Rosenblatt's algorithm as an energy minimization algorithm. And then we went on to say, okay, we can also extend this and, for instance, include additional terms such as one norms on the regularization, as you would often do, having regularizations on your objective, and then you would get something like a Rosenblatt ISTA, like iterative soft thresholding type algorithm, which doesn't require you to differentiate the activation functions. And we sort of compared this. We ran this on a classification example of MNIST. So it's just a toy example where we basically have a ReLU perceptron and basically a one-hot vector encoding of the outputs, and then the images are vectors of the inputs. So nothing that would actually really work well in practice, but it's just a proof of concept. And then we compared the objective to a couple of other algorithms where we just used stochastic gradient descent with constant or diminishing step sizes, and then also like a subgradient descent, gradient descent based ISTA, so where we don't use this new objective, but we always compare then all the solutions in the actual objective not with the new function, but with the old function. And surprisingly, we're actually doing, even in this objective, we're doing, oops, my cursor is gone. So we're doing even better. It's the red curve here. This is us. We're doing better. And you see here, for instance, with the subgradient descent with King, we don't have this. We have a quite normal natural behavior, and also in terms of accuracy, we do better. Obviously, this is more like proof of concepts and not like anything that's, oh, sorry, actually I said MNIST, but this is actually fashion MNIST. My apologies, that was my mistake. Otherwise the accuracy would be higher. Here, this is fashion MNIST. We did the same thing now. We did a classification example for like a less trivial network, so not just one layer, but so 5 layers where we start with the original dimension and then we bring it down to 64, and at the end bring it down to 10. And what we then compared this to are sort of different approaches. So the standard lifted network approach, which if you remember, just gives you an affine linear network, stochastic gradient with backpropagation, and then our approach. And in terms of training accuracy, I think this was, Victor, you can correct me, either 50 or 100 epochs for all models.
50 epochs, yes.
50 for all of them. And we get for fashion MNIST, so we get a relatively comparable training accuracy and also test accuracy, not quite exactly as well, but I guess if you iterate it for more epochs, this becomes this will approach the same numbers. But we also see that the linear network obviously doesn't perform by any means as well as the other networks. And so this table here, this is another one where we basically just have checked how many of the so how linear the network actually is, basically meaning like where entries actually really negative and where are they not. And then obviously the standard lifted approach, everything is very linear, whereas then in these approaches it's not. So we really utilize the nonlinear activation functions. And one outlook, what we actually really want to do are things like sparse autoencoders where we actually penalize the hidden variables. So where we would introduce regularization on something like the intermediate variables to, for instance, make something actually sparse. I was hoping actually I could include like a very sort of quick result, but unfortunately it's just an outlook. So the results are in progress. And therefore I want to conclude now my talk and basically just quickly say what we have sort of seen, which was we've discussed sort of distributed approaches, or had a bit of an introduction of what approaches are out there. Introduced this lifted-Bregman approach that avoids differential activation functions, but also doesn't have the limitations as the classical lifted-Bregman approach. Discussed the computational solution strategy and shown some preliminary numerical results. And as an outlook, and this is basically where I try to tie this now briefly to inverse problems. Oops, this was too quick. Why did that? My apologies. If we go back. So one important thing is to obviously extend the whole concept to other architectures, such as ResNet, which is not should be too challenging, but it's also not completely trivial. It will also limit the type of algorithms we could use. But what I'm actually also quite interested in is using the approach for fixed weights but unknown input to do something like an inversion of neural networks, and whether this would actually constitute a regularization in some sense. So this is my very, very little tying it to inverse problems, but there's definitely more hopefully to follow in this direction. And we have a conference paper on the perceptron case, and hopefully a full preprint available soon. And with this, I'd like to conclude, and thank you very much for your attention.
Thank you very much, Martin. A very nice talk. Are there any questions? Yes, Yuri.
Thank you very much for the talk, Martin. You mentioned this bi-convex problem that you get, and at least if the problem were quadratic, the optimality condition would be a bilinear form. I don't know if that probably changes in your case somewhat.
In this quadratic, it's bilinear. Oh, yes.
By means in terms of being linear in each.
Yeah, no, exactly. That changes in our case because we have the activation function in there, which also makes it non-linear. So that's why we always have to, do something gradient based rather than solving.
Sure. Yes, but at least in the quadratic case where it is bilinear, you could lift the problem and linearize the problem using tensor products. I was wondering if that could still be useful in your case.
Possibly. Haven't thought about it, but would definitely be something worth lifting it. I don't know. Yeah, we'd have to think about it. I don't have an answer straight away. So you just think of maybe clarify a bit on like you want to lift. What you want to lift like your matrices to tensors?
Well, the idea behind tensor products is that you linearize bilinear mappings. So something that is linear in arguments coming from different spaces can be used. Well, tensor products are basically they have the dual space of the space of bilinear, blah, 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 blah. And you can, by using tensor products, you can treat bilinear forms as linear objects in the tensor product.
Ah, I see.
You probably blow up the dimension, but still you retain, well, you obtain, sorry, linearity. And in your case, you would not have a bilinear form, but maybe you can still view it in the tensor product space.
Maybe, yeah. I mean, obviously, I haven't thought in this direction at all, but that would be the question. Maybe it's obvious that it doesn't work like that straight away, or there is an angle. I'm definitely happy to discuss offline. Thank you.
Thank you.
Any other questions?
So in terms of parallelization, how much computational benefit do you actually gain? Have you compared to SGD type approaches where you can actually parallelize?
No, it's definitely still on the list in the sense that on the to-do list. I mean, our motivation really came more from we've seen the approach, and we didn't really so much come from the like okay, how well does this compare just like the distributed in terms of distributed approaches, but rather how can we overcome the limitation? And also our focus is a bit more on, or our interest is a bit more on this, what I showed at the end, that we actually can. So I think the real benefit is actually more like if you try to incorporate regularization or regularity on hidden variables. And I think that stochastic gradient-based approaches are not very suitable to do that, because you have to, I mean, you have to obviously differentiate then also something like the one norm as a regularization, and you get like big Lipschitz constants and all this stuff. So I don't think that's actually really going well. So this is actually where we rather came from. So that's why we haven't really looked so much into the performance changes. But I mean, in this paper from Carrera, Perpignan and One, I mean, they have these tables in the paper where they compare their distributed approach to other approaches that were, I guess, state of the art at the time. It was from 2014, so it's already maybe a bit outdated, but also the other approaches. I mean, they have some comparisons, so maybe that's there. Hopefully find the answer in there, but I don't have an answer right now. But I would obviously expect that algorithmically, I mean, you can distribute it quite easily if you have enough of a cluster. I mean, I would be surprised if you can't utilize this in an effective way.
Okay, and also as a follow-up, have you tried activation functions that you can differentiate?
The hyperbolic tangent, for instance, actually, nothing. Victor, did you try anything computationally with like some hyperbolic tangent, for example, or mostly with the soft thresholding and the?
I think mostly with soft thresholding and really I haven't tried that.
So yeah, so actually we haven't really, but I mean we should, because one thing we also thought about is that with, for instance, hyperbolic tangent, one issue there is, even though it's differentiable, is that the derivative is scaled quite differently compared to the function itself, and then you get the vanishing gradient problems. So one hope would be we don't have to compute the gradient for something like this, that it's also beneficial. But yeah, we haven't done it. So that's a good suggestion. Thank you.
Any other questions?
Hi, thanks for the talk. I wanted to ask a small question, I think. Because you said that we were just now looking at the example of replacing the L2 norm with a Bregman loss. So in this function definition of L, would that, if you were to replace this L, if you were to try to replace some other norm with the Bregman loss, would that basically be changing the first term in the Bregman loss? Is that right?
Yes, you mean like I'll try to find the.
I think it was something before page 40. Or no,
you mean like basically, yeah, like
first term there, for example.
Yeah, you could potentially, yeah, you could potentially think about obviously replacing this 2 norm with something else.
Mm-hmm.
But the one issue is, or one thing that doesn't make it too trivial is that this whole term is also crafted or based or crafted according to the definition of the proximal map. Mm-hmm. The proximal map, the classical one, obviously uses the square 2 norm. Yeah. So if we have a more generalized proximal map, we can probably extend the concept then also to replace the function, the first function, with whatever function used in that generalized proximal map. The question there then is, do you still have, I mean, for this generalized proximal map, you would still probably require things like the Moreau decomposition, and there are definitely works that have more generalized Bregman distance-based proximal maps that can satisfy this, but it's not as straightforward or as trivial. But one thing that I also haven't said, which in practice everyone does, I simplified the notation a bit, was that often this term is only actually being used for, let's say, the intermediate layers, and then you still add a loss function on the output of your network that could be something completely different. So that we can do anyways. So if we want to have this not as restrictive. But yeah, but in terms of, say, if you have a for instance, proximal map as an activation function that is not a classical proximal map, but a proximal map in some other sense, and you really want to use this in your network, then this could be a good approach. So I think it's a good suggestion.
One quick one.
I was just wondering about training the model, let's say for one data set to the point that overfits to the data, like your method comparing to the other methods. Is it going to be the overfitting will be delayed by a bit because you put like constraints comparing to the others? It's just speculation.
That's a very interesting question. I wish I had an answer for this. This is something we haven't actually really looked into yet. So we have really focused mostly on the training problem and not so much on the effect on the validation problem, although obviously that's really the interesting problem ultimately. So whether this reformulation maybe also has a sort of regularizing effect in some way so that the validation errors are better or worse, or maybe, I mean, I think it heavily depends not just on the formulation, but then also how you solve it algorithmically. We had one example, which I didn't show here, but for the perceptron case where we solved it with ADMM. So we could actually solve linear systems in the algorithm, and then we would basically massively overfit because we would solve the training problem to really good accuracy. And it would actually then in terms of validation would be much worse. So therefore, I think it's a combination of these factors, like having this different loss, but also then how you numerically solve it will probably be answer to that question. But I have no real, unfortunately, no real comparison. So this is still, unfortunately, still unfinished in that regard. So, but yeah, thank you.
So I have a couple of questions for you, but I think since you all want to go for lunch, I think it's first go for lunch and then I will ask my questions offline.
Yeah.
But let's thank Martin and all the other speakers of this morning again. Outside as usual, and then we reconvene at 1:30.
Okay, so welcome back, everyone. Very happy to have Marta Beck to give the first talk this afternoon. So Marta is Associate Professor in Computer Science at UCL and a member of the Centre for Inverse Problems and the Centre for Medical Image Computing. So she's going to talk about on learning the invisible in PAT with flat directionally sensitive sensor. So please over to you, Marta.
Thank you very much. Thank you very much for the introduction and for the invitation. And it's been a wonderful workshop, even for the remote participants so far. So thanks a lot. So I apologize if my widgets come. I never managed to eliminate them. If they come, I'm sorry for that. I don't know how to get rid of these. I tried many times. Okay, so I would like to talk today about learning the invisible in photoacoustic in a very particular scenario with the flat directionally sensitive sensor, which is what I spend most of my time working on. And so this is joint work with my PhD student who is coming to the end of his PhD ball in Pan. And so this is an idea that has been popularized by Tatiana and Gita, Max, and Samuli and collaborators already in a certain way, mostly in the context of X-ray computed tomography. So this is kind of this is our take on this idea with the particular application in photoacoustic with this particular type of the sensor where certain things happen. So this is what we find exciting about this. And okay, so let me just go switch. Oh, but how do I switch my slides? Okay, so this is a very kind of very quick minimalistic introduction to the photoacoustic. So just in case you've never seen it before, so essentially we illuminate the tissue with the near-infrared pulse of light. This light propagates diffusively through the tissue, establishes some sort of tissue light distribution in the tissue, and this gets absorbed by the chromophores, and essentially this absorbed energy is our contrast. So the biologically this corresponds to the difference between the oxygenated, desoxygenated hemoglobin. So it is a kind of quite a relevant biological contrast, one of the appeals of photoacoustic tomography. Okay, so now we have this absorbed energy here, and this energy gets converted to the initial pressure in photoacoustic, in the process of that is called photoacoustic effect. And this initial pressure is now propagated in a form of the sound wave to the surface of the tissue. So this step from the initial pressure to being propagated through the tissue and being recorded at the set of the sensors on the surface of the tissue, this is our photoacoustic forward problem. Okay, so our contrast is the initial pressure. We record this initial pressure propagates through the tissue, is recorded as a pressure time series on the set of the sensors at the surface, and this constitutes our data. And I'm going to be very specific to this particular geometry that I have in a picture, meaning that I have a flat sensor sitting on the top of the tissue, and I consider the half space below that sensor, above what, okay, below here. And I'm going to solve the problem in the half space. I'm going to use the symmetry to get rid of the ambiguity that you get because of the half space. So you have to decide either you want the even or odd symmetry and to get rid of the ambiguity on the full space. And I'm going to denote the sensor with the curly S, and then all the variables that live on the sensor will have the subscript S. And all the variables that in this ambient space that we have here that are perpendicular to the sensor will be denoted with the subscript perpendicular. Okay, so that is just setting the stage. So let me formalize this as a kind of mathematical in mathematical terms. So we have a forward operator that acts on the compactly supported smooth C infinity functions in RD, which is my ambient space, and brings them to this compactly supported smooth functions of time and functions on the sensor. So the smoothness here is this is a technical kind of condition here, and this is enforced by using a smooth aperture in time. So this forward operator here boils down to solution of the initial value problem for the wave equation that I have here. At the bottom, so I have my wave equation, I have my initial values here, and so this is the absorbed energy that got converted into the initial pressure. So this is my initial condition here that is being propagated through the wave equation. So now I solve this equation and I record the pressure time series on the detector, and then so I record this pressure time series on the detector over time, and this is what is going to be my noiseless because it's coming from the model photoacoustic data. Of course, in the experiment they will be contaminated with some sort of noise. Okay, so I will also need an adjoint operator. So the adjoint operator essentially goes backwards, but it's not the inverse operator. So it can be shown that the adjoint operator to the photoacoustic forward operator is now a time-varying source problem for the wave equation with zero initial conditions, and the source term is essentially the data that I recorded on the surface or on the sensor, plugged back as a source backwards in time. Okay, so now I can run this source problem with this backward in time acting source, the data backward in time acting as a source, and when I run it for time t, then I'm going to obtain my adjoint solution. Okay, and then we also have an inverse operator. If the data is complete, then this is indeed an inverse operator. If it's not complete, then it is, let's call it approximate inverse operator. And so this is quite similar to the adjoint, but now instead of having the source term, I actually have the data backward in time plugged in as a hard constraint. Okay, so the source adds additively at the sensor locations, and this term acts overridingly at the sensor location. So there's a subtle difference between the two, but the philosophy is the same. You run this equation for time t and evaluate the solution at time t, and then this gives you your inverse solution. If you had complete data, that is indeed going to be your original. And speed of sound was nice. It is indeed going to be your original initial pressure. So now I'm going to make the following assumptions. I'm going to assume that I have a constant speed of sound. And as I already said, I'm going to assume the half space symmetries per planar sensor geometry. So I'm going now to look at these equations in Fourier domain. So it is well known that this is the solution to the initial value problem in Fourier domain, in terms of Fourier domain in space, and not Fourier domain in time. So it's also called cost propagator. So taking this solution, going completely to the Fourier domain, so changing also to the Fourier domain in time. And I'm going to switch to something that I call time normalized, speed normalized time, and then speed normalized frequency, just to get rid of the C essentially. So, but that is just a change of, a simple change of variables that is happening. So I'm going to use this normalization, so that you know. So, but changing from this formula essentially to the Fourier transform in time, and evaluating this at the detector instead of the whole space, I'm obtaining this relation here. Okay, and this is under the assumption of the half space symmetry. So this formula here has hard coded inside the half space symmetry, and of course the constant speed of sound. And so this formula gives me a relationship between the initial pressure in Fourier domain, complete Fourier domain, and everything space and time, and my propagated pressure over, propagated pressure on the detector. So essentially, this is my forward operator, okay, if written like that. So, and in fact, it's not, this formula didn't go undetected, but actually you have to turn it around so that you actually get, actually are looking for P0 in terms of the P hat. Okay, and this is well-known inverse formulation, and it is used by the practitioners routinely. And this is a stable formula, and so you can, if you have your data, you can multiply it by the inverse of this fraction here, and then you can perform the inversion in the Fourier domain. So now if you want to use this as a forward problem, however, you have the singularity to contend with. And this blows up, of course, when this quantity here approaches zero, and it needs regularization be used. Okay, so so we have used this in some form before. But let me plow on nonetheless. So formally to prevent this singularity from growing up, we have to satisfy this condition. And bear with me that I use the omega over c without the absolute value, because I do everything on half space that corresponds to the positive time and the positive omega, and the deal with the other side of things, which is here, using symmetries, assuming some symmetries. So that's why this is the notation. I don't have time to kind of go into every detail of it, but this is kind of the philosophy why there is no absolute value here. Okay, so so this is the assumption that has to be satisfied, and this corresponds to this condition when I plot the Fourier plane corresponding to the data. So this is my time. So this is a frequency domain, the data and frequency domain. So this is my time frequency, and this is my detector frequency. So this is the condition. Okay, so that's how it looks like. So this we have to be inside of this bow tie, and this is the range of the photoacoustic operator. Okay, so now this equation here, what essentially it is essentially a change of coordinates. It's essentially a change of coordinates between the Cartesian coordinates in a ambient space and the hyperbolic coordinates in the data space. Sorry. So that is what we can see in this plot here. So I plot the over this data space frequency domain, I plot the isocontours of the corresponding k-perp, which is my ambient space coordinate that is perpendicular to the detector, and then you can see that which points in this data correspond to which points in this ambient space. Okay, just by virtue of looking at the contours, how this contours. I have another plot later that maybe will bring it better out. Okay, so I should also note that the KS coordinate is of course common for both the data space and for the, so this is the coordinate along the detector, so this is the common coordinate between the data and the ambient space. So essentially we have this change of coordinates. So we have on one side, we have the depth vector in the ambient space, on the other side we have a vector in the data domain. And then we have the formula for k-perp that looks like that, and we have a formula for omega over c that looks like that. And these formulas come from the dispersion relation of the in the wave equation. So we have now the formula, and it's essentially just a change of coordinates. So let us study this a little bit more. So this is an example of how to look at it in the physical space. So in the physical space, I have a source. Let my source be away by r away from the detector. So this is my detector here, and this source emits a spherical wave, and this spherical wave kind of propagates towards the detector, and as the time elapses, the wave kind of impinges on the detector in the different planes, so different points. So at the very beginning, the very first part of the wave that will arrive will be here, and then as the time goes on, there will be the wave will arrive here, and then later it will arrive here, and so on. And when it arrives here, it's going to arrive under this angle, and then when it arrives here, it's going to arrive under this angle, and so on. Okay, so now when this spherical wave passes through the detector, of course it gets recorded, and if I just keep this to this wavefront view of things, so this is how my data wavefront is going to look like, corresponding to the spherical wave. Okay, so this is the part of the wave that immediately arrived here. Okay, and then this is the part of the wave. Then when the wave arrived at this point in the detector, so this is kind of what got recorded in the data, and there is a corresponding wavefront or tangent to this hyperbola here that corresponds to this wavefront that arrives at the detector. Okay, so that so as my wave time goes on, the angle theta gets closer to pi12, and my angle beta here gets closer to minus pi4. Okay, so essentially this is kind of the extreme is this asymptota here, and then so you have kind of the envelope of beta that goes from minus pi4, and then it can then changes here on the other side to pi4. Okay, so I have an angle of under which the wave can arrive and sits in between minus pi12 and pi12, and then the wavefronts in the data domain have angles between minus pi4 and pi4. And of course, to kind of the angle pi12 is never reached. So if we, as the time goes to infinity, the angle impinging angle of the wave gets closer to pi12. But just to be pi12, we would really have to move the source to the sensor itself, and this corresponds to the asymptotas. Okay, so this is the space domain, if you wish, view of the ambient space and of the data space. So now we can look at this wavefronts in a Fourier domain, which is to bring us back to the relationship that we had from the formula before. So they, of course, they have the same direction. So we can look at this wavefronts in the Fourier domain, and so they have this corresponding Fourier wavefront vectors, and we have a kind of the same type of a correspondence. And here now very easily we can derive the relationship between these two angles. And so we just observe, from geometrical properties, we really observe that the tangent of the beta hat, which is this angle here, is just the corresponding coordinates of the Fourier domain wavefront vector. And this is the tangent, okay? And then we observe that because of the definition, how we define this, that of course the corresponding wavefronts have to be at the same point in the detector. So we have we have this correspondence between the k as beta, which is this coordinate here, that is repeated here with the inverse sign, and then the corresponding k as theta, which is the coordinate of the vector impinging on the detector, and the bottom part comes straight from the wave equation dispersion relation, and so then we recognize the sign on the right hand side, and we get the relationship between this tangent and this sign, and now we can move it back to the vectors that we defined as vectors at which the wave impinge on the detector. Okay, so but these were the kind of the angles between the wavefront vectors, and these are the angles between the detector and the wavefront. Okay, so we have out of this is a bit of a complicated derivation or explanation. So we have this relatively simple relationship between the angles. Okay, so between the angle theta and the angle beta, and then there is just the one-to-one map that we call the wavefront mapping. So I mentioned this briefly, but so there is this the symmetry that underlies my forward operator in the Fourier domain is the even symmetry with respect to the sensor. And this has the consequence that for my initial pressure of the even symmetry for my initial pressure and the even symmetry for my vector P. So the pressure in the data domain. Okay, so there's the even symmetry with respect to the first variable. Okay, so this is the one that corresponds to the mirroring around the sensor. So this would have the consequence that formally, going back here, I would have another source here, and then the source would do exactly the mirror image of what this is doing, and it would give me the other side of the hyperbola here. Okay, so that is how the symmetric picture comes together. So summarizing, I now have these three operators in the Fourier domain that I kind of understand what they are doing. So I have this original relationship, and then I can use it as a forward. I can use it as an inverse, but with the blow up warning. I can use it as an inverse formulation, which it has been used, and I also can derive the adjoint, which happens to be this one in this notation. Okay, so now the question, I can hear you screaming, so why have you been doing time stepping and why it's not done like that? And that is the reason. So I guess that I would draw attention to the big plot in the center, which is the one that no one has seen, the path data that looks like that. So this is the path data obtained with this Fourier method. So what you see here is this kind of so as your angle approaches pi-half, you of course are approaching the singularity, and then you have a problem, and you see very kind of magnified aliasing artifacts. Okay, so of course now you could start to say you could maybe smooth this somehow, and it's possibly to some point there could be some possibilities that this could result in something equivalent, but that's actually not the subject of the talk. That's just for the motivation here. So and once you have this data, so this is the reconstruction that you get. Okay, so that there's a yeah. So I'm not showing you kind of, I'm comparing this always to the original image here. The reason for that is that this is a if I would use, for example, something like K-wave, this would smooth the data and would lose quite a lot of contrast. So these reconstructions here, however, you don't like them maybe because they have this kind of, you should see this aliasing artifacts being propagated back to the image, so they actually have a better contrast, okay? So they are more appropriately compared to this than to the original photoacoustic data. This is not saying that you cannot reconstruct the photoacoustic data with it. You of course can. So we have here opted for the minimized setup, so we kind of are not oversampling in time. You would have to adjust it. Okay, so okay. So and now if I, when I said that I have a limited angle sensitivity, what do I mean? Okay, so in the photoacoustic, as actually in X-ray as well, but I think in photoacoustic, it might be that most people think always about the other artifacts as the main ones. So if I have a finite sensor, I will get this typical artifacts that kind of look like that. Okay, so they kind of correspond to they're microlically quite well described, and they kind of correspond to spheres that are centered at the corners of the detector. So, so this is one type of the artifacts. So this is not the one, not what I want to talk about. So I want to talk about, I want to talk about the limited data. So the other type of the limited data are that you actually, when each sensor only sees wavefronts that come under, that impinge on the detector under a certain angle range of theta. So if I had ideal sensor, it could record anything from -pi-half to pi-half, but my non-ideal sensor will have some pi max that is between 0 and pi-half, and it will be smaller than pi-half. Okay, so for example, here's a pi-third, so 60 degrees. And then this, what happens then is that it's going to limit your range further. So this bow tie get further restricted to this red lines here, okay? And this corresponds to this pi third angle being cut out from your original P0. Okay, so I tried to visualize this here. So I have put in this coordinate planes, I have put isocontours of constant chi perp. Okay, so that is what it is. Okay, and this these are the same contours that you can see here. Okay, so that is so this cut off line here cuts out a bit of the P0. So we are kind of losing some of the P0 information, which you would expect with the limited data problem, and it corresponds to having a kind of more strict, more limited bow tie in the Fourier, sorry, in the data domain. So this I have this correspondence between the beta and the theta that we derive with this wavefront map, that this angle correspondence here. So from this comes this correspondence between the two. Okay, so right, so the kind of the wave can arrive only in a certain kind of under the certain angles, so that is just only giving rise to certain range of beta. So now when you look at this, then I have used now a slightly smaller angle, so that you kind of, it kind of corresponds to pi 4, so that you can see it better. And so now what you can see is that this limitation of this bow tie essentially takes us away from the singularity. And indeed, this is what we have done before to regularize the forward operator. So we have done this type of a cutoff, okay? So, but now in the limited data problem, and there it was a regularization, and it was kind of like a violation of the forward operator in a sense, because you have been eliminating parts of it, even though you wanted them. So now, however, in this limited angle problem, they are just not there. Okay, so the limited angle data problems regularizes this formula for us. So now we have the forward formula that is actually stable. Okay, and then the range of this formula is just this red region, the colorful region up to the red line, and you can work out the particular factor here. What is the bow tie? Okay, so good. So now I have these three formulas that I had before, that the only difference is that I evaluate them only on this kind of red restricted bow tie. And I will give them this extra angle symbol. Not great. Okay, so this is now how the picture that I was screaming not like that looks like. And actually now on the left hand side I have projected the data on the range, and of this I have projected this on the visible range. Okay, so then this is what you hope to recover, and I didn't quite compare that, but it kind of looks quite okay, and then the data also looks quite okay. So actually we can use the Fourier domain formulation to do the limited angle, and this has saved us order of magnitude in computation, because the time stepping makes the operator order of magnitude more expensive. Okay, so order of magnitude in terms of the side aspect of the domain. So I will introduce, so I have these angles, angular dependencies everywhere. I will need curved coefficients. This is kind of the frame I quite like working with. And then just recalling briefly the curvelet decomposition is computed in a Fourier domain using these trapezoidal functions here that have the scale direction. And there is a set of locations at which these curvelets are located. The low frequency, the lowest scale is isotropic wavelets essentially, and the whole system is built so that all these windows form a smooth partition of unity of the Fourier plane. And this is kind of the visualization of the curved tiling of the Fourier domain, and we are going to use the symmetrized version that puts equal these wedges here that are symmetric in terms of imposes Hermitian symmetry on them for the real function. And we use the implementation via roping. There is numerical isometry from the curved toolbox, and we will define a wedge restricted version of these by just restricting the computation of the curvelet to this gray domain, which is, we restrict the computation of the curvelets only to these directions that are in this, what we call wedge, okay? So that is with the long definition, but this is the gist of it. And so this in 2D, this would look like that, and in 3D, this would look like that. So this is the transform that we introduce, or the modification of curvelet transform that we introduce in terms of representing photoacoustic data. There is a couple of more subtleties there if you do that. So if you want to have a look, you are more than welcome to check out this one here, or look at the implementation on GitHub. So, but this is kind of the wedge restricted curvelet transform, and then the wedge restricted curvelet transform can be formally write as a composition of the projection operator and the standard curvelet transform. And the projection operator is the one that projects on this directions inside of the bow tie. And kind of originally we introduced this in this form that we had directionality at all final scales except for the core scale. The core scale was not directional, and it was mapped to itself. And here we also would like to introduce another version of it, which also has a directionality in the core scale by virtue of using a bow tie filter on the core scale coefficients. Okay, so the notation is slightly abusive here, but it just says that also the core scales we take into the directionality, because formally the core scale coefficients don't have directionality, but it just means that we take only those that are in the bow tie, and the picture kind of tells what we actually mean. So we just really virtually take in a Fourier domain, we apply this filter. And on the range of this, regardless how we define that, either this or the other one, so this wedge restricted curvelet transform is an isometry on its range, on the range of the project. Okay, so the effect of it is that this the standard curvelet transform, the restricted curvelet transform without the directionality in the lower scale just will eliminate the higher order higher scale coefficients outside of this pi-4 angle, and then additional directionality of the core scale will give you this typical. Probably you can't see it, but these are the kind of the limited view. Kind of with all the limited view artifacts. So this is what it's going to do to the core scale. Okay, and now projection. So what projection is affected by this different transform? So there's a standard curvelet transform. So it just it's an isometry. So when you have this restricted curvelet transform, then you will project on the final scales on the visible range. So this is the invisible part on the final scales that you're going to lose. And if you have the core scale directionality, then you actually will recover something that's kind of like the limited angle stuff that we know and love. Okay, so with this, we have now this. I'm going to use this fully restricted with the directionality in the core scale as well. So I can now have three things. I can have a perfect reconstruction by virtue of taking an original image and decomposing it in this restricted curvelet decomposition, and it's orthogonal complement. I can have the linear reconstruction of the visible curvelet coefficients, Okay, so then I'm going to use this equivalent of the time reversal lifted to the Fourier domain and so on. So this is the kind of pseudo-inverse kind of thing, A hat dega. And I can have a fully blown nonlinear reconstruction with this restricted angle operator, of course, to recover the visible, and then it goes back to the works by Eugen Fricke and Todd Quinto, and so the same was used by the guys here in the kind of tomography, but with their versions of the operators that they use, radon transform and so on. So okay, so the postulate is to learn the invisible, and then why? So the reason is to how I'm doing time really bad, no? Okay, do I have 5 more minutes?
Between talks, I think the talk's supposed to finish at 10 past, but there's like a 10-minute gap, so we can sort of go into that.
Okay, I think I will. Okay, I will be okay. Thank you. So, so why to learn the invisible? So the reasons are kind of separation between the data and learn prior. Okay, so you kind of reconstruct what is in the data, and then you put in what is only in what you can't see in the data. You put as a prior, kind of learned prior. And so the other thing is that once you have the separation, so the invisible is out of the range of the forward operator, so it doesn't. You don't need to iterate with the forward operator with the network. Okay, so the whole kind of stuff of should I do unrolling, should I post-processing doesn't apply, because you just do post-processing. Okay, it's equivalent. Okay, so I will need for the network that we formulate, I will need one decomposition here. So that is with what we timely called corona decomposition, and the name just that couldn't quite come up with a different name. But okay, so the gist of it is that it is like the filter bank that is being applied in the curvelet transform if you disregard the directionality. Okay, but so I have my image, and then and one scale of this is doing the following. I will put it in a Fourier domain. I will take the high pass filter, and I will take the low pass filter. Okay, and then the low pass filter lives on a smaller dimension. I can back project it to the image in a smaller dimension, and the high pass filter in the Fourier domain kind of lives on this annulus here, but in the image domain it will live on the bigger domain of this type. So I have this decomposition, the high pass and low pass, and I can put them back together by kind of padding this guy here in the Fourier domain with 0, and then adding this to this guy in the Fourier domain and going back to the image domain. Okay, so this is what I call corona decomposition. So it's essentially scale decomposition. And then this is the effect of the one level of corona decomposition. So this is the high pass component, it's the low pass component. You can see the difference in sizes. So this is when you put them back into the image domain. So the difference between the corona decomposition and the curvelet coefficient is visible here on the kind of, this is a single curvelet in the visible range, and this is the corona of the visible range, and kind of this is on the intermediate scale, and this is kind of the core scale, but because I use this both, I think they are the same. Okay, the core scale. If I use the not bow tie low core scale, then they would be different. Okay, so good. So now I have this network, and it's essentially like a unit, but I have my image split in scales in this corona decomposition situation. So it means that I have my visible channel and then my invisible channel. So that I have 2 channels at each scale. And at each scale, I put in the corona decomposition of the image. So I put in like, like these guys, okay? In the image form. I put them into the network, and I put them at the different levels, okay? So they don't pass all the way down. So, and then it kind of propagates unity style, and but after the convolutions here, I will use the corona decomposition, and I will put the high pass fall back to the right, and I will put the low pass to the lower, propagate the low pass of the lower scale. So this kind of is my max pooling kind of variant, but it obeys this decomposition that we are using. Okay, so this is the how the downscaling and so on works. And you do the same on the next scale, and then and the core scale, and then at the kind of subsequent the visible and invisible coefficients come in at different scales, and they are being back propagated to kind of through the unit to the output here, and the output is all images upscale to the finest scale. So they are upscaled by padding in the Fourier, so padding in the Fourier domain. So we have this this network here, and then we have a corresponding unit that we made a unit that just gets the visible part of the image and should output the complete image that we try to make as equivalent as possible to the corona net. Okay, and then we train it on a set of ellipses that look like that, and we have a generalization check on a ball that look like that. And let me draw attention to one thing. So the ball here is put like that, so that the limited angle of the operator disables the artifacts of the limited sensor. Okay, so this is constructed like that. We didn't quite manage to have a good training set that obeys that. Yes, I should finish. Yeah.
Yeah, please. So we don't run into time. If you can finish in the next 60 seconds, that would be great. Thanks.
Second, sorry, I thought that you said I have till 20 past.
No.
So the next talk starts at 20 past, and so if you want time for questions.
Yeah, but just let me 2 minutes, okay? And then I will answer a question very quickly. So so basically we have we have this training set here, and then kind of we try to to learn the invisible. Okay, so that we have two scenarios. One is we learn from the perfect visible, to map from the perfect visible to the invisible, and from the imperfect visible to the invisible. And so these are my perfect perfect visible invisible coefficients, and this is what I learn. Okay, and this is kind of the error. And then in the speed of kind of here, it's not very good to see anything. So but you kind of see that you kind of learn something, because it kind of looks similar, and the error is kind of smaller. And so this is when you put it together. So this is how it looks like. And then so on the right is ground truth, on the left is the corona net, and in the middle is the and corresponding unit, reference unit. Okay, so then and you can see that the error is a little bit kind of so it is in favor of our network here, and then the generalization is even more pronounced. Okay, so the range here is less than half of the color bar here. Okay, so we kind of, especially the corona net does especially well for the generalization, and this is belabored again in this on the data on the test set of these ellipses, that kind of we kind of the corona net wins everywhere for the test set, and except for the SLIM, and we're everywhere on the generalization, which is just the one ball. Okay, so then I just showed this second picture here. So that from the imperfect visible to this one, that come from the L1 reconstruction. So this is kind of the corresponding error plot, and the corresponding generalization that is like 10 times, the color scale is now 10 times smaller. So the generalization is much better here. And then this is kind of the corresponding table. So the corona net wins. So we all know that corona wins. So there we go. Thank you very much, and sorry to overrun.
We probably have time for a couple of quick questions. Does anyone either online or physically present have anything to ask? Maybe I can ask a quick question. So you started off with some assumptions about the symmetry of the sensor and of the, I think it's on the speed of sound. I mean, how kind of important are they in terms of?
Oh, they are absolutely crucial, because the Fourier from PDEs in Fourier domain require constant coefficients to start with, and then the assumption of the symmetry is but the assumption of the symmetry is something that comes from the comes from the geometry. Okay, so now the speed of sound. Okay, so if we don't have any indication of the speed of sound, which is usually the case if you don't have another modality hooked up to the photoacoustic scanner, and it's only now that we are starting to build combi scanners, so that you have an ultrasound that you actually could have a speed of sound. So even though I spent a fair amount of my time previously computing things for the different speeds of sound, this is an important part of the deal, that for the practical data very often we assume constant speed of sound. So that's not very restrictive. In many applications, it is also correct, because the changing speed of sound is in particular small animal situations and so on. So many of the vasculature images actually are good enough with the constant speed of sound. The geometrical assumption for the sensor, it is restrictive in the sense that it is for this particular geometry, and the Fourier formula that you get, it's simpler that you would get for other geometries, I think. I mean, we haven't executed that per se, but I forgot the details, but there is something that doesn't simplify for the type of spherical sensor and so on in a similar way. Okay, so you have the same kind of situation that your data range and lives in this type of bow tie, for example, the circular sensor, but there is something about the Fourier formula that doesn't simplify, so it is restricted in this way, yes. So to the sensor, but sensor is very important. The flat sensor is very important because this is the one that gives you this high resolution imaging.
Okay, thank you, sir. We have 1 minute before the next talk, so for no further questions, and I guess thanks again, Marta.
Thank you.
You have a 60-second break. We'll resume shortly.
Yes, I'm just going to show.
Oh, yeah. Do you have any announcements?
Yeah. And then she interpreted that as disinterested. So yeah, until
We can use this.
So yeah, after that you can offer some regulatory courses and all. That's what, but then at the same time, probably be not. Okay. She suggested that we go to the and see what courses are already offered.
Okay, so I think we'll make a start, try and keep on time. So our last speaker of the day is Nicola Kovacsky, and Nicola is a PhD student in Caltech with Andrew Stewart. So I guess you probably traveled the furthest to be here. Yeah, and so it's going to talk about learning operators for forward and inverse problems.
Yeah, thank you. Thank you so much for having me. It's really a pleasure to be here and to give a talk in person. So today I'm going to talk to you about some ongoing work that we've been doing, which is on learning operators. And most of the talk is going to focus on forward problems, but so basically how you design a surrogate model that is consistent in function space. And we'll use some deep learning ideas to do that. And I'll talk both about sort of practice and the theory that we have developed so far and what's missing between the two. And in terms of inverse problems, I'll talk about some applications to inverse problems. We haven't done so many applications to inverse problems, but I will discuss the ones that we've done, and also some theory that relies on some inverse problems, hopefully, if I have time. Okay, so just to set up. Yep, so I'll just give you the problem setting and I'll sort of motivate why we want to learn operators the way that we want to learn them, and sort of what people have been doing currently in machine learning, and that may be why that's such a good idea. From there, I'll give you first one possible approach to this, which is a model reduction approach. So this is going to yield a linear method of approximation. But so numerically, this will yield a method, and this method will be a linear method. But also from a point of view of theory, this reduction to a linear method will give us sort of a way to prove a lot of universal approximation theorems that hold in function space. And I'll give also an application of this method to a mechanics problem. Then I'll sort of try and do go beyond the linear setting and make a nonlinear method of approximation. And this will be this kernel network approach. So this will be like a lifting of deep neural networks to function space. So how that makes sense, and yeah, what that means, and this will give a nonlinear method of approximation. But again, for theory, you'll be able to reduce this to a linear method of approximation to be able to prove universal approximations, and we'll also be able to get some rates for certain PDE forward problems. For this, but again, and then for that, I'll give an application to basically solving Navier-Stokes and then doing an inverse problem for Navier-Stokes. And so everything in this first part of the talk will basically be concerned, theory-wise, will be concerned with approximation theory. So how many parameters you need to approximate a particular operator without considering data. In this last setting, I'll go the other way. I'll consider data, but I'll focus only on linear operators. And then I'll show you some theory on what you need, how much data you need to learn infinite dimensional linear operators from noisy data. Okay, so that's generally how this is going to go. Okay, so the problem, we assume we have some map, phi dagger, and this is a map between two separable bounded spaces. Actually, separable is not fully enough. You also need approximation property. I'll talk about that more later. But this is the general assumption I'll use. And I'll assume that I have data, so x and y. So x and y here are functions. So I always think of them as just functions without discretizing. Okay, so infinite dimensional objects. Okay, both, and I'll assume I have n of them. And for the purposes of theory, they will either, the x's will either be sampled IID from measure mu that's supported on x, or that will somehow come from a compact set K that lives inside of X. Okay? And the goal again will be to learn a operator. So from some finite dimensional parameter space P, I want to somehow design an operator which maps X to Y. And of course, I want to find the best parameters given my data afterwards. And in the first part, again, I'll focus on how much, given some psi dagger, what kind of how big does P have to be for me to learn psi dagger to an appropriate level, and then later I'll focus on how big does N have to be. Same thing. And the key, the sort of the philosophy of this whole talk and of this whole work is to design your architecture and then discretize. So design something on a continuum level and discretize it later. That way you get something that's consistent. And so this is an example of why you might want to do this. Just an example of an operator. You have an elliptic PDE, simple elliptic PDE, and maybe there's a lot of operators to categorize here. You can maybe even care to map from F to U, or you map from G to U, but both of those are linear maps because this is a linear PDE. Particular nonlinear operator that categorizes A to U. One thing here, L infinity is not a separable Banach space, but you could consider a separable subspace for the coefficients, for example. It's not really, we're not going to consider usually the whole function spaces anyway, so that's not a problem. And again, we're going to care in terms of approximation error, we're going to care about either the error in this Bachmann norm, where we draw the samples, the input samples from a measure mu. So the reason this could be hard is because mu could be unbounded. So mu could have support on the whole of X, in which case you have to somehow use its decay properties to get something, or we're going to care about a complex. with some example. And so what happens if you sort of don't first discretize? If you first discretize and then just apply a neural network, basically what happens is that your error goes up. So this is what I'm showing here is the previous problem. We've taken 1,000 data points and we've taken a convolutional neural network from paper. That's a very 19-layer convolutional network. And I've just taken different resolutions, so different discretizations. So you can think of, this is like a 400 by 400 grid or a 200 by 200 grid of the exact same data. Data doesn't change. And in each step, you retrain the convolutional neural network and you see how well it does. And so you're not testing it, you're not training at some resolution and trying to test it another. You're retraining it every single one, and then you see how well it does and your error grows. And you expect that because the way the convolutional neural network is designed is to be local. The filters are discretized locally. So of course, if I plug in an image that's discretized more finely, the spatial sort of support of the filter is immediately smaller. So as I go to the continuum, the spatial support of the filter of the convolutional network becomes just a delta function, so it becomes completely local. And so you expect this to happen. And so what really I would want to do in this is design an architecture that can flatten this. So why would I want to flatten this? If you think about traditional numerical methods like finite elements, you would expect this to go down, right, as I increase my resolution. But that's also because if I do finite elements, I'm also increasing the number of parameters in my architecture as I increase the resolution, right? If I resolve function higher, then I have more finite elements I need to resolve. So that's more parameters in the architecture, so to speak. Here, we're talking about a fixed number of parameters that doesn't change. They can work on any resolution and achieve a constant error. So that's really what I mean by something that's open.
Yeah. If you made the number of layers grow so that your receptive field of your network was fixed.
Yeah, sure.
Would it be flat? Would it go down? Or?
It would somewhat flatten it, but then you get more and more parameters, you get deeper networks, and then harder to train, and so it's, yeah. Okay. So the first approach I sort of want to show is the smaller reduction approach. So again, this is going to yield a linear method of approximation, and I'll relate it to sort of a reduced basis method. It would be easy to see. So what's the idea? The basic idea is just to take your infinite dimensional problem and somehow reduce the dimension with proper dimension reducing maps. So this is just the whole idea in a picture. Psi dagger is the thing I care about. And to approximate it, I'm going to reduce its dimension basically of my input. So I'm going to take a map F, which reduces the dimension to something finite dimensional. Then I'm going to do all the work of psi dagger, all the nonlinear parts of psi dagger inside a finite dimensional map. And then I'm going to live that back out into the infinite dimensional space. Yeah. So in sort of just in equations, this is like what people call autoencoders in machine learning. You get two maps which compose the identity approximately, of course, because there's something finite dimensional between them on both levels, as well as the X and Y level. And then you just connect you'll call the latent space with something finite dimensional. Okay, so when can you expect such a decomposition to give you sort of existence of F, Y, and psi? And the answer is quite general. So if I have two separable Banach spaces with the approximation property, so approximation property just means that for every compact set of the Banach space, there exists a finite rank operator which approximates the identity. So not all separable Banach spaces have this property, but usually the function spaces we care about do. And so those are the two assumptions I have to take on X and Y. And on psi here, psi dagger, I'll say that it's continuous. And if this is the case, then for any compact set, I can find bounded linear maps, Fx and Gy, for some unknown dimensions, dx and dy, which are finite, and a continuous map, phi, so that the composition that I showed you before approximates psi dagger up to epsilon. Okay. So I need really very little assumptions for the composition I showed you before to work. I need a Banach space with AP, and I need a continuous map. And in fact, so if I want to now do the approximation instead in a Blochner norm, where I average over this measure, then I can actually drop the continuity assumption on SciDagger. I only need measurability. But what I incur is I can no longer work in a bounded space setting because I have to take X, well, I have to take Y at least to be a separable space. And this is because, well, when you design these maps, you need to somehow control a uniform error across the whole space. And a Hilbert space lets you do that through like a little L2 isomorphism. Otherwise, yeah, I don't quite see a way to do it in bounded space, but maybe there is. But at least for the current theory, this is what we have. Okay. So this is when those two exist. And so this leads itself to a very simple architecture now. I haven't said how to compute anything, right? I haven't said how to compute F or G. The simplest way to do it is through PCA. Right, so PCA makes sense on any Hilbert space. So to do this, I have to assume both X and Y are Hilbert spaces. And so all I have to do now is compute. So the F map will be LX, which just computes my coefficients, my PCA coefficients under the measure mu, and my bases. So my GY will essentially be a computation of the bases under the push forward of SciDagger, their mu. And so I just need data to compute both of these, right? X and Y pairs, nothing else. And then in the middle, what was called phi before is this map alpha, which now I can just make a neural network and then learn its parameters theta, right? So this gives immediately an architecture that was implemented just by using a PCA type encoder. Okay. So this is, yeah, this looks exactly like a reduced basis method. And it's a linear method of approximation because you approximate in these m-dimensional subspace of the Hilbert space Y. Right. And of course, it's a non-intrusive reduced basis method because once I have my pairs of functions X and Y, I just train my alpha J, which is a neural network. And then for any new thing, I've pre-computed the PCA coefficient. So I can always, for any new input, I have bases, so I can always project onto PCA coefficients. And I again pre-computed these from data. So all I need to do is run this forward. So in terms of, you have a grid size of size n, then this is a method that will compute forward in linear time, so in n steps. And I don't need any knowledge of the PDE to do this. Okay. So you can prove that, again, there is a universal approximation theory for this. This basically combines the result I showed you before and also says that PCA will give you basically consistent bases. There's nothing really more to this result. So if you compute everything, if you compute F and G with PCA, and then you can find some neural network so that this Bochner error is as small as you want, then here it averages over the data in the PCA. You can also prove this with high probability over the data in the PCA if you want. Okay. So again, this is just, it's an existence result. So it's an approximation theoretic result that says really nothing about the data or the parameters yet. So eventually I'll have some theorem about the parameters, but nothing about that yet. Okay, so I'll just give you an example of this working. So again, I'm back to Darcy. So this elliptic PDE, I'm going to consider, I'll consider it with a fixed right-hand side, which is 1, and a 0 near the boundary. And I will consider coefficients which come from a threshold at Gaussian random field. So the measure mu that the A's come from is a Gaussian random field with a Neumann boundary that has then been thresholded. So everywhere that it's positive, it's taken the value 12, and everywhere that it's negative, it's taken the value 3. Right? So it's a piecewise constant random field. And this is what the U's look like if you solve it. This PDE. And like I promised you before, we can now flatten the initial curve. So what you get from this plot is essentially that one, you can get pretty low error on this problem. So even with so this uses only 1,000 training examples, which is very little data in machine learning. you can still solve this problem really well. You're completely independent to the resolution of your input. So that the curve is flat, and usually as you increase the reduced dimension, you also reduce your error. But you have to be quite careful with this, because eventually you will actually start to increase your error, and that's because you have a fixed number of data. So if I'm using a fixed number of data, like 1,000, which was the previous plot, I increase the reduced dimension that I'm using up to a point where it goes down and then starts to go back up. And that's because the neural network is solving a non-convex problem with a fixed amount of data. It becomes harder and harder as you increase the dimension. And so eventually you're going to start to do worse unless you add more data to your problem. So if you add more data, then of course you push all these points down and you flatten out eventually. So you always have to be careful with how you relate the reduced dimension to the amount of data you actually have. So there's some optimal sort of thing that you don't really know a priori. Okay, so this is this linear method, and I'll just talk about it quickly about an application of this method to a problem in crystal plasticity. This is essentially a homogenization problem of magnesium. So you want to complicated PV where you want to essentially learn the deformation of a block of magnesium when it's hit with something, or when it's thrown to a wall, or some sort of simulation, some sort of physical simulation is done to it. And the way we do this, we put it in a homogenization framework. So we look at a microscale structure of magnesium that's periodic. And the way the method is used is through what people in mechanical engineering call FE squared. So so you do finite element calculations twice. Basically, you calculate the deformation at each microscopic cell all throughout the material, and then you take that information and then you put that into the whole block, and then you can do a finite element calculation on the entire block. So that's what they call it FE squared. And what we do is instead replace the inner cell calculations with this machine learning, and then still do a finite element calculation on top. So now you only need a single finite element calculation for the whole material, and this seems to work pretty well. So I don't actually have reference calculations for this because they take much too long to compute. People don't have, I'll show you the numbers in a second, but this is this piece of magnesium being hit with what is really a bullet at different speeds, and you see how it deforms, and you can plot sort of the pressure field, the stress field of the material throughout. And this tells you, when it will fracture or any kind of properties you'd like to know about the material. It's just another test. You take a piece of magnesium, you throw it against the wall at different speeds, and you kind of just see what happens to it. You can see the faster you throw it, the more it comes out. So the more it deforms on the edges and the more stress there is there. And the reason you actually have real calculations is because of this. So the periodic RV is how you actually solve this homogenization problem. And you can see that to do a single time step on, okay, this is on one CPU, of course, takes up 10 to the 6 seconds for the previous two things I showed you. So you need a cluster to run for about a month to actually compute reference calculations, and we didn't do that. While if you use this machine learning approach, you're incredibly fast, and you can just do this forever. So this is why this is kind of useful, and why I guess mechanical engineers would want to use this kind of approach. Okay. Okay. So in the second part of this talk, I'm going to talk now about a nonlinear method of approximation, which will lift the concept of a neural network to infinite dimensions in a very simple way. And I'll sort of describe to you why. So I'll breeze through this. Okay. If you have a solution manifold of this knapsack dagger, but it's a very nonlinear manifold, then you need a very, very large linear space to be able to approximate it well. And so you don't want to do that. You want to actually approximate the manifold in a nonlinear way. Okay. So that's the short motivation as to why we want a nonlinear method. Okay, so how do we get a nonlinear method in function space? We'll take classical neural networks. So these are, we've seen them many times during this whole workshop. Our classical neural network starts with an input X, and then iterates by applying some linear transformation, which is just a matrix, AL, to the previous layer, adds a bias, and then applies a point-wise nonlinearity, and it does that L times. Then you get your output at the end. So there's a very simple way to live that to infinite dimensions. First, so I'll start with the activation functions. The activation function you can lift just by thinking of it as an Nowitzki operator. So again, x is a function, s is a spatial variable. So it acts as an operator at a spatial point x just by composition point-wise. So this can be, so you don't need any type of continuity of the evaluation operator to define this. You can define this sort of Lebesgue almost everywhere, and as long as sigma is linearly bounded, you can also prove that it acts as an LP to LP operator. So there's not much restrictive on sigma to define this, and then so the meatier part of what you'd want to do is how do you lift this matrix to a infinite dimensional operator, and a very sort of clear way to do that is through a kernel integral operator. So instead of applying directly a matrix, you instead integrate against the kernel kappa L. So kappa is a function that you now want to learn. So instead of learning directly coefficients of a matrix, which are just some set of numbers, instead you learn a function kappa. So you can parameterize this as a neural network or whatever else you want. Or I'll show a few different ways of calculating, and then you apply it just by the kernel integration through it. Yeah. And this whole sort of thing gives you a neural network now in infinite dimensions. So one thing to notice about it is that maybe I'll go back for a second. If I do this and my y at the end, so I have this operator AL here and a capital L here would be the application of this kernel integral operator. Notice that this still gives me something at the end that's linear. In particular, it relies in the range of the last kernel integral operator. The difference, though, between sort of traditional linear approximation methods is that it's no longer finite dimensional. So in a traditional linear approximation method, the linear space which you approximated is some finite dimensional space, but this is the range of this operator is infinite dimensional. So even though it's a linear space, it's an infinite dimensional linear space. And furthermore, you can also non-linearize it by applying something at the end, which is now a learned Nowitzki operator. So Q is now also has a spatial dependence. So it's a Curry-Darty function, and it defines that you learn it. So everywhere throughout the architecture, you have sigma, which is fixed. So it's like ReLU. And at the beginning and at the end, you can add two more operators. Well, you don't have to add it at the beginning, but really to make it a nonlinear method, you should add it at the end, which again acts as a Nowitzki operator. And now you actually learn what Q is. Yeah. So this defines now a neural network that is fully consistent in infinite dimensions. And I've also added this, this sort of ResNet type term here, which you could have or you don't have to. Anyway, and it's a pointwise term. But of course, you can generalize it to be a non-pointwise term. The reason I've added it is I want to make a connection. So recently, transformer architectures have been incredibly popular in machine learning. For language models in particular, they've been state of the art with GPT-3 and forget the names of all the others, but billions of parameters, and people have been able to really like generate text. So I just want to show you that transformers are really kind of a special case of this if you make your kernel nonlinear. So if you make the integral transform a nonlinear integral transform instead of a linear one with a very specific choice of the kernel, then you can obtain transformers back. And that makes a lot of sense because when people design transformers, they design them to work on sequences, right? And they want to work on sequences of arbitrary length. And that's the same thing as being discretization invariant in some sense, right? Being able to work on functions that can be discretized in any arbitrary way. Okay, so I just want to, I'll just take one layer update of the architecture I showed you before. The input is x, which is a function on RD taking values in Rn. And all I have to do is take my integral kernel transform here. I'm going to take my kernel and instead make it depend on X. So the kernel itself is going to depend on my input in a very nonlinear way. So not only through the spatial variables X and Z, but actually through the values of X at S and Z. But that's only pointwise. In fact, it's going to depend on the whole of X. So the kernel kappa subscript X here is going to be defined as a scalar function, gx, which again depends on the entirety of X and through its pointwise values at the spatial points S and Z times some parameter V. So V is just a matrix here. Notice that V is an n by n matrix, and n has nothing to do with the discretization of the region. N is just the size of the input vector function. Okay, and then I take the way I define G is basically through, so the way, why does it depend globally on X? Because it does so through a integral on X. And this is like a sort of a continuous version of softmax, if you look at it, plus parameters Q and K. Yeah, so basically you do a softmax of X, then you evaluate it against another parameter function V. And yeah, so Q and K are also parameter functions here. So if you know something about transformers, you know that Q is the queries function, K is the keys function, and V is the values function. And those are all the learned parameters of the transformer. So if you just do a Monte Carlo approximation of this, you get exactly the transformer vector. Okay. Okay, so what can you prove about these architectures? Okay, so I'm now going away from the transformer and back to the linear integral transform. So the reason sort of, now I've sort of made things more specific. I've taken a kernel integral transform. So that means now I have to work on function spaces that are on domains. So I can't work on general Banach spaces anymore. And I'll work on function spaces that have bounded domains. And I'm going to assume that they're all Lipschitz domains. Okay. So so what you can prove is, so I mean, the topology of the function space that you pick changes how you do the approximation. So it's not like for a regular neural network, you just have some subsets of Rn, and it doesn't matter what the subsets of R. You can prove one universal approximation theory kind of covers everything, but here you have to consider every function space that you care about separately because the topology of the space changes the approximation. Yeah, and so as a universal approximation theorem, what can you prove? You can prove that if your input space is LPE or a Sobolev space or continuous functions, and your output space is similar, including the continuously differentiable functions, and your side dagger is continuous, then over compact sets, you can approximate uniformly. So there exists an architecture that you can do that. Similarly, in the Wagner space setting, again, you can take your input space to be Lebesgue, Sobolev, or continuous, your output space to be Sobolev, but now a Hilbert space, like I mentioned before. And again, you have a universal approximation theorem that says you can approximate anything over a measure, even with an unbounded domain. Okay. Okay, so that's generally what you can approximate. So how do you compute? I haven't said anything about computation. Generally, this is not super cheap to compute because you have this sort of n squared term here. So you have to find a way to deal with that when you're actually on a grid and you discretize. So we've had a lot of ways to compute. You can basically restrict the supports of these kernels to make them smaller. I mean, that doesn't overall lower your complexity. It just it does it by a constant. You can do general Monte Carlo sampling inside this domain. Again, that only lowers the computational complexity by a constant. Things that will asymptotically lower the computational complexity are things like the fast Fourier fast multiple method, but that requires sort of some assumptions on what kappa can be. And the thing that has been particularly successful is actually going into Fourier space. So if I assume that my kernel kappa is now translation kernel, and I parameterize its instead of parameterize, I basically parameterize it directly in Fourier space with some fixed number of components. Then I can compute this integral explicitly and directly in Fourier space by a fast Fourier transform. And now that's an n log n method, right? So I reduce the cost significantly. And also it's something that works quite well in practice. Okay, so I mean, when I make this change, of course, the theory that I just showed you doesn't hold anymore, because everything relied on the kernel being a function of s and z. Now it's a function of s minus z. So that changes what you have to do. But again, you can prove universal approximations. So because we do things in Fourier space, it's natural to sort of work on the torus. But this theorem also says that you can extend things outside of the torus. So this theorem has really two statements. So again, I'll start with a bounded Lipschitz domain that's going to be contained inside a periodic box. So I can take a box, take any domain, embed it in a box of any size. And now this theorem says two things. The first thing it says is that there is a linear periodic extension operator on any Hilbert-Sobolev space. So what this means is that there just exists an operator that will take a functional domain and produce a function that looks exactly the same inside the domain, but is periodic on a box that is bigger than the domain. Okay. So that's the first statement of this theorem. And the second one is that if I have a continuous operator on this a side dagger, again, acting between these two Hilbert spaces, then for any compact set of this space, I can find one of these Fourier type parameterizations. So I'll call this an FNO, a Fourier neural operator. There exists one so that I can approximate, again, uniformly with a composition through E. But again, I'm not telling you how to compute E. So if you have a periodic function, so if you're just working on the torus, then E is just the identity. Otherwise, you have to sort of find some way to compute E. But it does exist and is linear. Okay. So, okay, again, none of this is anything about rates. In fact, okay, in general, for general operator side dagger, the rates can be arbitrarily bad for this problem. So you can find examples where the rates of approximation are sort of doubly exponential, if you like. So you need, if epsilon is the tolerance, you need something like epsilon to the minus epsilon to the minus epsilon. That blows up, doubly exponentially. But for particular cases, you can actually prove that you can get efficient approximations that do beat the curse of dimensionality. So here's first I'll take Darcy on the torus. I'll assume that my coefficients are sort of regular enough. So I have some embedding, and I'll assume that they are coercive. Okay, so these are the two assumptions. And again, I'll take the operator to be the one mapping A to U. Okay. So then for these types of coercive coefficients that are regular enough, which I'm denoting A lambda S here, there does exist this Fourier type FNO architecture, which approximates uniformly over this set, and the rates of approximation beat the curse of dimensionality. So there you can notice that there is no curse of dimensionality here because D is the domain, so only the physical domain, and K is for the smoothness of the right-hand side. And no other constants show up. So you're doing something in an infinite dimensional way without that infinite dimensional thing showing up. And you can do that. You can do the same thing with Navier-Stokes or Euler. Of course, you have to assume that so AS here now is a set of initial conditions where the solution exists and is bounded and doesn't blow up. So you just make that as an assumption, and then once you have such initial conditions, then you can again prove that you can find this type of FNO where your rates of approximation beat the curse of dimensionality. Yeah? And the essential method of proof for these is emulation of pseudospectral methods. You write out how a pseudospectral method will solve it, and you look at your sort of operator type method, and you see exactly how you can mimic it. Then you can match those two up and get precise rates. Okay. Okay, so I'll just give you a quick example again of this working on a simple equation. So there's burgers with viscosity in 1D. The problem that I care about is mapping the initial condition u0, the solution u at time 1. So I'm not doing a time dependent problem. I'm basically getting rid of the time by just mapping the initial condition to some final time that I fixed. And that's how the theory for Navier-Stokes worked as well. The operator is again a mapping of the initial condition to some final. Okay. Just an example. So this is a Gaussian random field as an input, and you get this sort of characteristic, almost, well, not a shock because you have viscosity, but almost shock-like solution. Okay. And the output, and again, this is a very overloaded graph. I apologize about that, but the thing you care about is this bottom line. So this is this FNO operator. Again, so we compared it to a bunch of other things, and sort of it does the best, and it also flattens. You can do this at any resolution of a function, and you get the same consistent result. Yeah, so it's a true operator method. I'm going to skip that. Okay, so a better application to turbulent flow. So now I'll do this same thing, but I'll do it for Navier-Stokes. So the operator I'm going to care about is this one. So I look at Navier-Stokes, and I look, so this is in the Leary form with the projection operator, and I'll look at the a forcing of, I don't know what it is in the Leary form, but it's a Kolmogorov flow. So a forcing of like -4 sine, something that just continuously inputs energy into the like Fourier mode. Okay, so that's known as a Kolmogorov flow. And the operator of interest will be the one that maps the vorticity. So the vorticity is the curl of the velocity u, and the goal of the operator will be to find given some initial vorticity, the vorticity at a later time. And in fact, we're going to do this in two ways. One will be just as a direct mapping, and one will be with a mapping through time. So you can actually approximate the vorticity at all times by viewing this as a sort of a 3D method. Yeah, you start with some initial vorticity here, and this is the sort of ground truth Kolmogorov flow. It happens then at the bottom, you predict the whole sort of trajectory of the flow. This is only down with 1,000. Okay, this is in a Reynolds number of 1,000 with 10,000 data points. You get about a relative error of 3% in H1. So this is also, the error also calculates the derivatives. You get a pretty small error in H1. And again, you can also use this if you train on sort of small grids like here. You can actually evaluate on large grids, and you can actually do that through time as well. So in this example, everything is trained on a 64 by 64, I think by 30 grid or by 50 grid, and it's actually evaluated on a finer, so by 80 grid in time. So you've done super resolution in space time. Yep. Okay, so here's finally an inverse problem. So the inverse problem I'm considering here, and I'm running out of time, but the inverse problem I'm considering here is again Navier-Stokes. I want to recover the initial vorticity by sampling the solution at a later time at a few number of grid points and then adding noise to them. So this is the vorticity initially, this is the vorticity at a later time. I observe it pointwise at these small grid points, and I add some noise to them. And then the goal is just to use this as a surrogate model to recover initial vorticity. I do this in an MCMC framework, so I formulate the problem in a Bayesian way, solve it with MCMC, and again, the sort of punchline is that this will only take 2 minutes to sample 50,000 of these, while if you just use a two-spectral solver, you need about 30 hours. And 50,000 samples is very few for a problem of this type. It's really not converged. You need on the order of millions to get it to converge. So these are, I'm just showing the means of the posterior, and the means look about identical, but again, they haven't actually converged, and that's because the spectral solver will take weeks. Okay, so I'm gonna skip this now because I clearly don't have time. The punchline of this is that if you consider linear operators, you can prove that you need more data to learn unbounded operators than you need to learn compact operators. So in the context of inverse problems, a compact operator is the forward operator, while the unbounded operator is the inverse operator. So this tells you that you need less data to learn the compact operator or the forward operator. So in some sense, it's a better idea to directly learn the forward operator and then plug that into some sort of method solve your inverse problem than it is to directly try and solve your inverse problem with a data-driven method. I mean, this is very, this is only for linear problems, and yeah, but that's the basic idea. But then you can prove this exactly rigorously, and you can get exact rates for the operators in terms of the amount of data. Okay, so I'm gonna finish now because I'm out of time. Thank you very much.
Very much. Are there any questions? Okay, you're right.
Thank you very much for the talk. I'm wondering about your error estimates or convergence rates for those PDEs.
Okay.
We had a few talks in this workshop and also in this program by Y0E, for example, and by I believe, on function spaces of neural networks, like these F1 spaces in Francis Bach's paper. They also go under different invariant spaces.
Yep, invariant spaces. Yeah.
And one of the things that came up in these talks is that, especially in relation to PDEs, is that it is hard to say when a solution of a certain PDE lies in these spaces. Do your results on these approximation rates relate to that?
No, they don't. So that's quite different, right? So in those settings, you have a solution to a PDE, and you parameterize that solution by a neural network. Then you try to see how many parameters you need in your neural network to get this solution. So this is quite different. I'm actually parameterizing the operator itself, and then trying to find the operator. So it doesn't, yeah, it's really not related.
Sure, but does the operator have to be in a certain class, a certain space of operators?
No, only continuity with a given. So I'll go back to the result. The general result is, so this is the general result. So the operator has to only be continuous, no other assumptions on the operator, and a mapping between any of these spaces. And then you have these results. And then, okay, to get actual rates, you need to actually, specify what the operator is, like here. But I mean, this operator is, it's just given by the PDE. It doesn't need to be in any variant space. Yeah.
Thank you.
Yeah, thank you very much. Great talk. And our team takes a lot of inspiration from your papers. And if you now relate the last part of the first one, if you go to Darcy's equation and input U and output A, so solve the inverse problem. Did you do some numerical examples of that?
Look at that. This is the slide I skipped.
Okay.
Yeah, so we actually just tried that. I mean, this is, okay, this doesn't really do the inverse problem as it should. It basically just flips the problem. So you do A to U, now you do U. And this is kind of what you get. So this is the ground truth. And this is the sort of reconstruction. So this is just one example of the reconstruction. It does pretty okay. And then this is this Fourier thing. So, it's working with something that has a Neumann boundary and is non-smooth.
So they used the Fourier method.
Yeah.
They didn't use the reduced order model from the first part.
You could use the reduced order model, but we haven't done that. That will not work well.
Yeah, that's right.
That definitely will not work well. I agree.
And
Yeah,
the
because it's a linear method.
For the first part is if you talk to the finite element people, they say, oh, great results.
Yeah.
But go to higher accuracy, go to 10⁻⁶ relative error, 10⁻⁸, and then get problems matching.
Sure, I agree with that.
Did you reach high accuracy, say if you go to 10⁻⁶ relative error?
Oh, but then it's the same question. How would you read 10⁻⁶ error with a reduced basis method?
Exactly.
Yeah, you wouldn't. I mean, it has the same issue, but it gets rid of the issue of you actually having to solve the system every time you do any coefficient. Right. So if I do a reduced basis method and say even on a linear equation, I still have to invert for every new A.
But then it's fair to say if you want to go to the highest precision, that's not the method to take.
Yeah, I would agree. It's not the method to take. Yeah, I would agree with that. Yeah.
Oh, that's great.
Yeah, probably already started. I don't know this area at all. Very, very interesting. Probably a really stupid question, but you're showing that the, say, finite element case is very, very slow. Neural network case is fast with train on data.
Mm-hmm.
But it's not like some of the other problems we've been looking at where the data's come from somewhere else. This is fully simulation based. So why can't you design a better finite element method? This is just as good.
Yeah, well, why can't you design a better finite element method?
Better simulation method. Why do we need neural networks?
You could design a better simulation method, and then you should use it to generate data for this method, because it will never be faster.
What is it about? So in trying to solve this problem, what is it about the data approach that as opposed to a clever fast maths method?
Okay, so let's think about it this way. Let's think about it in terms of the a time-dependent problem, right? So if I try and solve a time-dependent problem like this one, with a let's say absolute spectrum method, how would I do that? I would discretize in time, and then at every step I'll have to solve a system and so on and propagate that right forward. So I'll have to, the time discretization here and the amount of sort of steps I have to take will be very, very large.
Maybe I'm asking it in the wrong way. I'm not saying why are current methods so slow. But I mean, from a philosophical point of view, everything has come from the model, and you've come up with a method that through simulating data and then training is super fast. That suggests that there exists a method that is super fast.
Yeah, I agree. There possibly does, but this is also not only applicable to things that come from models, right? Everything I've said is data agnostic, so you could do this on images or on things that don't have direct models.
Yeah, no, but I was just interested.
Philosophically, philosophically, I agree with you, but that doesn't mean you can come up with it.
Okay.
Okay, do you have any more questions? Either Yuri?
I'm happy to ask it offline too if we're out of time.
I think we've probably got time for one more question. Yeah.
It's a quick one about the super resolution you mentioned in one of your last slides. Do you have any error estimates for that? It's true, you can learn something on false images.
No, we don't have error estimates. Theoretically, no, we don't have error estimates.
I think they could be obtained.
I think they could be, yeah, definitely. So some of this FNO work actually does consider a grid. So it says that, given a certain grid size, for anything larger, you can do this well. So I think you may be able to do some theory where you flip that. So for anything smaller, maybe how much error you incur. Yeah, but we don't have that yet.
Okay, so I think we've reached the end of the day. So thank you very much to Nicola and to Marta and to all the speakers today. We resume tomorrow for the final day. I think it starts at 11 o'clock UK time.